What if I told you that everything that has ever happened in the universe, every supernova explosion, every collision of galaxies, every moment of your own life, has left a permanent, physical mark on the fabric of reality? It sounds like something out of science fiction, but some of the greatest minds in physics have seriously proposed that the cosmos itself might be one giant, dynamic memory system. Think about that for a moment. It means the universe isn't just an empty stage where events play out and then vanish. It's more like a vast cosmic ledger, silently recording every single occurrence across space and time. This isn't just a poetic idea. It's grounded in real scientific inquiry, and it challenges everything we thought we knew about reality, memory, and our place in the grand scheme of things. The brilliant physicist John Wheeler once suggested something truly mind-bending. He said, "The universe does not just happen, but is built up from an accumulation of elementary acts of observation." What he meant is that the universe might actually be shaped and defined by the events that take place within it. Every action, every observation leaves a kind of residue, an imprint on the cosmos that never fully disappears. It's as if the universe is constantly taking notes, preserving the story of its own evolution in ways we're only beginning to understand. From the faint afterglow of the Big Bang to the mysterious echoes near black holes, there are clues everywhere that the cosmos has a memory, and that memory might hold the key to understanding existence itself. In this video, we're going to explore one of the most profound and awe-inspiring ideas in all of science, the concept that the universe stores memory. We'll trace how events imprint themselves across space-time, how the past might literally be written into the present, and how the cosmos could be whispering its history to us, if only we know how to listen. By the end of our journey, you won't look at the night sky the same way again. You'll see it not as a silent, empty void, but as a living archive filled with stories spanning billions of years. So come with me, let's uncover the secrets of how the universe remembers and discover what those memories might tell us about everything, including ourselves. So what does it actually mean for the universe to possess a memory? We have to step back from our everyday understanding of the word. For us, memory is a biological or digital process, the firing of neurons in our brain or the ones and zeros stored on a hard drive. But cosmic memory is something far more fundamental. It's the idea that information is never truly lost. It is a physical property that must be conserved, a law as unbreakable as the conservation of energy. Every event, no matter how small, leaves an indelible mark on the fabric of reality, a kind of permanent record etched into the cosmos itself. This shifts memory from a passive recording to an active participant in shaping the universe. The past isn't just gone, it's physically woven into the present, influencing the structure of everything from the largest galaxy to the smallest particle. One of the most compelling frameworks for understanding this comes from a revolutionary idea in theoretical physics known as the Holographic Principle. Proposed by physicists like Leonard Susskind and Gerard T. Hooft, this principle suggests that all the information describing everything within a three-dimensional volume of space, every star, every planet, every person, can be entirely encoded on its two-dimensional boundary, much like the data for a three-dimensional hologram is stored on a flat, two-dimensional surface. Think about the event horizon of a black hole, a spherical surface that somehow contains all the information about the objects that have fallen inside. The universe itself might operate on a similar principle, with the entire cosmic history projected from the vast boundary of observable space. This isn't just a nifty trick of geometry. It implies that the universe is fundamentally an information processing system, and the space-time we experience is a projection of that data. To grasp how an event imprints itself, consider a simple, powerful metaphor. When you drop a stone into a still pond, the impact is momentary. The stone sinks and is gone. But the ripples it creates spread outward, traveling across the entire surface long after the stone has disappeared. Those ripples are the residue of the event. They carry information about the stone's size, the force of its impact, and the precise moment it hit the water. In the cosmos, events create their own kind of ripples in the fabric of space-time. A supernova explosion sends out shockwaves of energy and matter. The birth of a star creates complex magnetic fields. Even your own life, the electrical signals in your brain, sends out an infinitesimally small but non-zero effect on the gravitational field around you. These ripples interact, combine, and persist, creating a complex, interconnected web of information that forms the universe's enduring memory. To truly hear the universe speaking its memories, we must learn to listen not with our ears, but with instruments that can feel the very fabric of reality trembling. One of the most profound and direct ways the cosmos records its history is through gravitational waves. These are not ripples in water or vibrations in the air. They are literal ripples in the four-dimensional fabric of space and time itself, predicted by Albert Einstein over a century ago. Imagine the universe as a vast, still pond. When a cataclysmic event occurs, something of almost unimaginable power, like two black holes spiraling into each other in a final, violent dance, it's like dropping not a stone, but a mountain into that pond. The impact is so immense that it sends shudders through space-time, creating waves that travel outward at the speed of light, carrying an encoded story of the event that caused them. For decades, these waves remained a beautiful but unproven theory. That all changed in September 2015, when one of the most sophisticated scientific experiments ever conceived, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal that would rewrite textbooks. The signal was the faint chirp, a rising frequency that lasted a fraction of a second, from the merger of two black holes over 1 billion light-years away. Think about that for a moment. The event itself happened when Earth was home to nothing more than single-celled organisms, and the ripples it created traveled through the void for over 1 billion years before finally washing over our planet, where we were finally advanced enough to catch them. This wasn't just a detection, it was the universe delivering a message from its deep past, a memory preserved perfectly in the undulations of space-time. Nobel laureate Kip Thorne described these gravitational waves as carrying information about their origins and about the nature of gravity that cannot be obtained otherwise. By analyzing the precise shape and frequency of these waves, scientists can perform cosmic detective work. They can determine the masses of the colliding black holes, their spin rates, and even the distance they traveled. It's as if the waves are a detailed fingerprint, uniquely identifying the event that created them. This transformative ability allows us to reconstruct history, to witness events that are completely invisible to traditional telescopes. With every new detection from observatories like LIGO and its European counterpart, Virgo, we are adding chapters to a silent, ongoing history book written not in ink, but in the geometry of the universe itself. Each wave is a permanent echo, proving that even the most violent cosmic catastrophes are not forgotten, but are instead etched into the very structure of existence for all time. But if gravitational waves are the universe's way of sending us messages from specific, violent events, there is another, far more ancient and all-encompassing memory system imprinted on the entire sky. This is the cosmic microwave background radiation, the oldest light in existence, and it acts as a flawless fossil record of the universe's very first moments. Picture the universe not long after the Big Bang, a searing, dense plasma so hot that light couldn't travel freely. It was constantly scattered, trapped in a swirling fog of primordial matter. Then, about 380,000 years after the initial expansion, something monumental happened. The universe had cooled and stretched enough for atoms to finally form, allowing light to break free and travel across the cosmos for the first time. That first burst of light, that initial flash of emancipation, is what we detect today as the CMB. It's the afterglow of creation itself, and it has been traveling for 13.8 billion years, carrying with it a perfect infant photograph of the entire cosmos. This ancient light is far more than a uniform glow. With incredibly sensitive instruments, we can detect tiny, minuscule variations in its temperature at differences of mere millionths of a degree. These tiny ripples are not random noise. They are the cosmic equivalent of a barcode containing an immense amount of information about the early universe. Each slight temperature variation corresponds to a region of slightly higher or lower density. These are the primordial seeds, the gravitational blueprints from which everything we see today eventually grew. The slightly denser patches had a stronger gravitational pull, attracting more and more matter over billions of years, eventually collapsing into the vast cosmic web of galaxies, clusters, and superclusters that define the large-scale structure of our modern universe. In a very real sense, the pattern of galaxies we see today is a direct, magnified reflection of those faint imperfections in the newborn cosmos. The universe remembers its own initial conditions with astonishing fidelity. To read this cosmic archive, we have sent our most advanced messengers into space. The European Space Agency's Planck satellite is a premier example. A time machine that spent years meticulously mapping the CMB with a resolution finer than 1/10 of a degree across the entire sky. Think of its work like an archaeologist carefully brushing dust from an ancient, fragile manuscript. Planck didn't just map the temperature, it also measured the polarization of this ancient light, which provides an even deeper layer of information about the very first instance after the Big Bang, potentially even revealing the fingerprints of gravitational waves from the inflationary period. The data from Planck and missions like it have allowed scientists to determine the universe's age, its composition of dark matter and dark energy, and its rate of expansion with unprecedented precision. It is the most detailed baby picture ever taken, and it tells us not only where we came from but also hints at the ultimate fate of everything. A powerful way to understand the CMB is to compare it to the rings of an ancient tree or the layers of ice in a deep core sample from a glacier. Each ring in a tree records the environmental conditions of a specific year, how much it rained, if there was a drought, if the temperatures were unusually high. Similarly, each layer of ice traps tiny bubbles of ancient atmosphere, preserving a literal sample of the air from thousands of years ago. These are physical records of the past stored in the present. The cosmic microwave background is precisely that, but on the grandest possible scale. It is the universe's own ice core, a permanent, all-sky snapshot of what it was like at a specific, crucial moment in its history. It is light acting as the ultimate, indestructible record, proving that the universe doesn't just have a history, it has a permanent, verifiable receipt for its own birth. Now we arrive at one of the most perplexing and revolutionary ideas in modern physics, a concept that forces us to question the very nature of reality and information. For a long time, black holes were thought to be the ultimate cosmic dead ends, the universe's most efficient shredders. According to classical general relativity, once something crosses the event horizon, it is lost forever to the outside universe, its information presumably crushed into the central singularity. But in the 1970s, Stephen Hawking made a stunning calculation that turned this entire picture on its head. He discovered that black holes are not truly black. Due to bizarre and complex quantum effects occurring right at the edge of the event horizon, black holes should actually emit a faint glow of particles, now known as Hawking radiation. This means black holes slowly lose mass and energy over astronomical timescales, eventually evaporating completely. This incredible discovery, however, created a monumental problem that physicists have been grappling with for 50 years, the black hole information paradox. The rules of quantum mechanics are built on a foundation of unitarity, a principle that states information is never truly lost. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. Hawking's calculation initially suggested that the radiation leaking from a black hole was completely random, carrying no information whatsoever about the material that had fallen in. So, if a black hole evaporates entirely, vanishing from existence, what happens to all the information that defined the stars, planets, or spaceships that fell into it? It would seem to be irretrievably erased from the universe, violating a fundamental law of quantum physics. This paradox creates a deep crisis, a direct conflict between the two pillars of modern physics: Einstein's theory of general relativity, which describes black holes, and quantum mechanics, which governs the behavior of particles. If both are correct, how can they disagree on something so basic? The search for a resolution to this paradox has led to some of the most imaginative and mind-bending proposals in theoretical physics. One prominent idea is black hole complementarity, which suggests that from the perspective of an outside observer, information never actually falls past the event horizon. Instead, it is scrambled and encoded onto the surface of the horizon itself, much like the holographic principle we discussed earlier. Meanwhile, from the perspective of an astronaut foolish enough to dive in, they would pass through the horizon without incident, at least initially. Both perspectives are considered correct in their own frames of reference, complementing each other without contradiction. This implies that a black hole's event horizon is not a destructive boundary but a transformative one, a surface teeming with quantum information. This line of thinking, however, led to another startling paradox: the firewall. If information is being encoded on the horizon and radiated back out, the calculations suggested that the horizon would not be the smooth, empty space predicted by Einstein. Instead, it would be a searing wall of incredibly high-energy particles that would instantly incinerate any object attempting to cross it. This presents a new dilemma. Either our understanding of Einstein's equivalence principle is wrong, or our understanding of information is incomplete. The debate rages on, forcing physicists to re-examine their most cherished assumptions. The most exciting modern developments suggest that Hawking himself may have been on the cusp of a solution later in his life. Newer calculations indicate that the Hawking radiation may not be completely random and thermal after all. Through incredibly complex quantum entanglements between the inside and outside of the black hole, the radiation leaking out might actually be subtly imprinted with the information of what fell in. It would be like burning a book. To a casual observer, the book is gone, reduced to ash and smoke. But a hypothetical, infinitely powerful being could, in principle, collect every particle of ash and molecule of smoke and reconstruct the entire book from the information preserved in the arrangement of those particles. The information wasn't destroyed, it was transformed into an excruciatingly complex form. This implies that black holes, far from being cosmic information shredders, might be some of the most sophisticated memory storage devices in the universe. They don't annihilate the past, they absorb it, process it, and over near eternity, perhaps even return it to the cosmos in a new quantum language. the event horizon acts as a dynamic quantum hard drive, preserving the information of everything it consumes. The evaporation of a black hole wouldn't be a deletion of data, but its ultimate and final backup, scattered across the universe in the form of Hawking radiation. In this view, even the most extreme and destructive environments in the cosmos contribute to the grand, universal ledger, ensuring that not a single byte of information is ever truly lost. While black holes and the cosmic microwave background show us memory on the grandest scales, there is a far more subtle and pervasive mechanism at work, operating in the quantum realm at the very foundation of reality itself. This brings us to the bizarre and beautiful phenomenon of quantum entanglement, a connection so profound and instantaneous that it baffled even Albert Einstein, who famously dismissed it as spooky action at a distance. At its heart, entanglement is a process where two or more particles become so deeply linked that they lose their individual identities, forming a single, unified quantum system. What happens to one particle immediately influences the other, no matter how vast the distance separating them, whether it's across a lab bench or across the galaxy. This isn't a signal traveling faster than light. It's something even stranger, a correlation that seems to transcend space and time entirely, suggesting that the universe is fundamentally interconnected in ways we are only beginning to grasp. The reason this spooky action is so crucial to our story of cosmic memory is that it creates a permanent, unbreakable record of a shared past. When two particles become entangled, it is always because they interacted at some point in the past or were born from the same quantum event. That moment of connection forever ties their fates together. The information about that initial interaction isn't stored in either particle individually, but in the relationship between them. It's as if the universe at that precise moment made a note that these two particles are a matched set, and that note is written not on a page, but into the very fabric of existence. Even if you separate them by billions of light years, that relationship persists. Measuring one particle doesn't just tell you about its state, it instantly reveals the state of its distant partner, accessing information about their shared history that was created long ago and far away. To make this abstract idea more concrete, consider a simple but powerful metaphor. Imagine two identical books written in a complex, unique language. You take one book to the farthest edge of the galaxy and leave the other on Earth. If you open the Earth book to page 302 and find a specific word, you instantly and absolutely know that the exact same word is on page 302 of the book on the other side of the galaxy. The books themselves didn't communicate. The information was encoded in their shared origin, in the fact that they were printed from the same master copy. The knowledge was non-local, existing in the correlation between the two objects rather than within either one alone. Entangled particles are like these books. Their shared past is the master copy, and measuring one instantly reveals the content of the other, proving that a memory of their connection is preserved within the quantum framework of the universe. For decades, this was a philosophical debate, a thought experiment highlighting what many assumed was a flaw in the quantum theory. That changed because of a brilliant physicist named John Stuart Bell. In the 1960s, Bell devised a practical test now known as a Bell test that could determine whether these spooky connections were real or just a reflection of our incomplete knowledge. The test sets a very specific mathematical inequality. If local hidden variables, secret, classical information carried by the particles were responsible for their correlation, Bell's inequality would hold true. But if quantum mechanics was correct and the particles were truly connected non-locally, the inequality would be violated, experiment after experiment, using everything from photons to atoms, has confirmed that Bell's inequality is violated. The spooky action is real. Entanglement is not a mathematical abstraction. It is a genuine physical property, a fundamental feature of how the universe operates. This has staggering implications. It suggests that the universe is fundamentally woven together with threads of quantum connection, a vast, invisible web of correlations that records countless past interactions. Every time particles interact and become entangled, a new link is added to this web, storing information about that event in a distributed, non-local way. This isn't memory as a static recording. It's a dynamic, active network of relationships that defines the quantum state of the cosmos. It provides the underlying mechanism for ideas like the holographic principle, where information on a boundary defines the volume within. The connections between entangled particles on that boundary could be what builds the geometry and content of our three-dimensional reality. The potential of this quantum memory is now driving a technological revolution in the form of quantum computing. A classical computer bit is a 1 or a 0, a simple switch. A quantum bit or qubit can be both 1 and 0 at the same time, a state known as superposition. But the real power emerges when you entangle multiple qubits. In a state of superposition, 2 entangled qubits can represent 4 states simultaneously. 3 can represent 8, and so on, with the power growing exponentially. This allows a quantum computer to perform an astronomical number of calculations in parallel, solving problems in minutes that would take classical supercomputers longer than the age of the universe. It does this by effectively exploring every possible path at once, and that power is directly harnessed from the quantum memory of entanglement, the system's ability to maintain and process the complex correlations between its parts. So, from the tiniest particles to the architecture of reality itself, quantum entanglement reveals a universe that is not a collection of separate objects but an integrated whole, with its history written into a vast, interconnected network of quantum relationships. It is a subtle, pervasive form of information storage, a silent testament to every interaction that has ever occurred, proving that the past is never truly gone, but is instead intricately woven into the present, waiting to be read. But if quantum entanglement weaves a subtle web of memory at the smallest scales, the universe's most dominant yet mysterious components operate on a canvas of unimaginable vastness, potentially holding the ultimate keys to cosmic information's fate. We're talking, of course, about dark matter and dark energy, the invisible giants that together make up about 95% of everything in the cosmos, yet whose fundamental nature remains one of science's greatest puzzles. While we can't see or directly interact with them, their gravitational influence is undeniable, sculpting the cosmos and dictating its expansion. It's within this shadowy realm that some of the most profound questions about universal memory reside, questions about permanent preservation versus eventual erasure. Let's start with dark matter, the universe's invisible scaffolding. We know it's there because we can see its gravitational grip on galaxies, holding them together as they spin at speeds that should otherwise tear them apart. This mysterious substance doesn't emit, absorb, or reflect light, but it forms vast, diffuse halos around galaxies and immense, filamentary structures that span the cosmos. One compelling speculation is that these dark matter structures could act as passive gravitational archivists. Imagine a dense knot of dark matter, its immense gravity warping the space around it, an effect we call gravitational lensing. This warping doesn't just bend the path of light from distant stars, it can also magnify it, acting like a colossal cosmic telescope. In doing so, it could potentially trap and preserve information. The light from a fleeting cosmic event, like a supernova, would normally fade and disperse, but if its photons travel through a region of intense dark matter lensing, their paths could be twisted and focused in a way that creates a delayed or amplified echo of that event, effectively storing a faint copy of the information within the gravitational landscape for eons. It's a form of memory not written on a surface, but etched into the very geometry of space-time by an unseen hand. Now, contrast that with the role of dark energy, which presents a far more ominous prospect for the permanence of cosmic memory. Dark energy is the name we give to the mysterious force causing the expansion of the universe to accelerate. It's not just expanding, it's expanding faster and faster every moment. This acceleration has a profound consequence for information. As space stretches, the wavelength of light stretching with it lengthens, a phenomenon known as redshift. Over enough time, this redshift becomes so extreme that the light from distant galaxies will eventually shift out of the observable spectrum entirely, fading from view and becoming undetectable. But it's worse than just things becoming hard to see. The accelerating expansion threatens to push everything beyond a cosmic horizon. In the far, far future, every galaxy outside our local group will be carried away by the stretching of space at speeds greater than light, disappearing beyond an event horizon from which no information can ever reach us. The universe will become a collection of isolated island universes, each completely unaware of the other's existence. This leads cosmologists to a chilling ultimate fate for the cosmos called the heat death or the Big Freeze. In this scenario, the universe continues expanding and cooling forever. Stars burn out, black holes slowly evaporate via Hawking radiation, and all energy gradients, the differences that allow any work or processing to happen, even out. The universe reaches a state of maximum entropy, a lukewarm, featureless sea of particles where nothing ever happens again. In such a state, information isn't destroyed in the quantum sense, but it becomes so hopelessly scrambled and diluted across an infinite volume that it is effectively erased for any practical purpose. It would be the universe's ultimate memory wipe, a final forgetting on a scale so vast it's difficult to comprehend. Yet, even in the face of this seemingly inevitable erasure, theoretical physics offers tantalizing escapes. Some theories suggest that information might not be lost but could instead be conserved in higher dimensions, realms beyond our familiar four of space and time. In string theory, for instance, our universe could be a three-dimensional membrane, or brain, floating in a higher dimensional space. Information that seems to disappear from our perspective, like matter falling into a black hole, might actually be encoded on this higher dimensional brain, forever preserved just out of sight. Other ideas venture into the realm of the multiverse, proposing that our accelerating universe is just one bubble in a vast, frothing cosmic foam of universes, each with its own physical laws. In this view, information lost from our universe might simply be translated or transferred into another, becoming part of a grander, multiversal memory system we cannot access. Ultimately, the roles of dark matter and dark energy in the story of cosmic memory highlight the beautiful, ongoing tension at the heart of cosmology. We are piecing together a narrative of the universe using the faintest of clues, grappling with forces we can only infer and concepts that challenge the limits of our imagination. Dark matter might be a silent guardian of information, while dark energy might be its eventual eraser, or our current understanding might be completely upended by a future discovery that unites these shadows into a new, coherent theory of everything. This uncertainty isn't a failure. It's an invitation to the greatest detective story of all time, a reminder that the universe still holds deep secrets about how it remembers and how perhaps it never truly forgets. Now we venture into one of the most bizarre and futuristic arenas of physics, where the very concept of a stable, unchanging state of matter is turned on its head. This brings us to the strange and wonderful world of time crystals. Forget any image of a glittering gem. A time crystal is an entirely new phase of matter, one that moves and oscillates in a repeating cycle, not in space, but in time, and it does this perpetually without any input of energy. It's a structure that breaks what physicists call time translation symmetry. Normally, the laws of physics are the same at every moment. An experiment you run today should yield the same result if you run it tomorrow. But a time crystal is different. It picks a specific rhythm, a preferred tick of the clock, and it maintains that rhythm forever, making it a potential candidate for the universe's most perfect and permanent memory device. The theoretical foundation for this astonishing idea was laid by Nobel laureate Frank Wilczek in 2012. He asked a profoundly simple yet radical question. Could there be a form of matter that is in its ground state, its lowest possible energy state, yet still exhibits perpetual motion? Classical physics screams no, as it would seem to violate the cherished laws of thermodynamics. But Wilczek, working in the quantum realm, realized that in a closed quantum system, such a thing might be possible. This wouldn't be a machine that creates energy from nothing. That's impossible. Instead, it's a system that exhibits stable, periodic motion without any energy loss, like a clock that never needs winding because it's not actually doing any work. It's just locked into an eternal, unwavering quantum rhythm. The profound implication for cosmic memory is staggering. If you can encode information into the repeating pattern of a time crystal, say, by making one oscillation a 1 and the next a 0, you would have a storage medium that could, in theory, preserve that information indefinitely, even in complete isolation. It would be immune to the ravages of entropy that eventually scrambles all other forms of information. This isn't just a theoretical pipe dream. In recent years, this exotic concept has leaped from the chalkboard into reality. Teams at Harvard University, Microsoft Station Q, and the University of Maryland have successfully created time crystals in the lab using sophisticated setups like chains of ytterbium atoms suspended by lasers or systems of nitrogen vacancy defects in diamonds. These aren't metaphors, they are tangible, observable objects that behave exactly as the theory predicted, ticking away with relentless regularity. Think of it as the ultimate cosmic backup drive. Imagine a probe constructed from a time crystal material being launched into the void. Billions of years later, long after the civilization that built it has turned to dust, that probe would still be there, and the information encoded in its rhythmic quantum dance would be perfectly preserved, a permanent testament to a moment in history. It represents a way for the universe to mark time itself, to create a persistent residue of an event that never fades. This cutting-edge research is opening a portal to understanding how temporal information, the when of things, might be physically encoded into the fabric of reality, suggesting that the universe's memory might not only be about what happened and where, but could also preserve the precise rhythm of when it all occurred. Now let's turn our attention to one of the most visually spectacular and energetically extreme processes in the universe, a phenomenon that acts like a cosmic branding iron, searing information across interstellar space with unimaginable force. Across the cosmos, certain celestial objects become natural particle accelerators of mind-boggling power. We're talking about supermassive black holes at the hearts of active galaxies, rapidly spinning neutron stars known as pulsars, and even some binary star systems. These engines don't just sit quietly, they fire out colossal, focused beams of matter and energy astrophysical jets that scream across space at nearly the speed of light. These aren't gentle streams, they are the universe's blowtorches, and they leave behind some of the most permanent and readable scars on the fabric of space-time. The scale of these jets is almost impossible to comprehend. Picture a beam of energized particles stretching not just across a solar system, but across millions of light years, often far exceeding the size of the galaxy that hosts them. These jets are born from the incredible dynamics around these extreme objects. For a supermassive black hole, it's the frenetic, superheated material of its accretion disk, matter spiraling inward at nearly light speed, that gets caught up in powerful magnetic fields. Not all of this doomed matter actually falls in. Some of it gets channeled and focused by these magnetic fields, launched outward from the poles of the black hole in a tightly collimated beam. It's a cosmic escape act of monumental proportions, a testament to the fact that even the most voracious objects in the universe don't just consume, they also create and expel, leaving their mark on everything they touch. These jets act as cosmic sculptors, and their medium is the thin gas and dust that floats between stars, known as the interstellar medium. As a jet plows through this material, it doesn't just gently push it aside, it violently excavates it. The jet rams into the gas, creating a powerful shock wave, a cosmic sonic boom, that heats the material to millions of degrees and sweeps it up, carving out vast cavities or bubbles in the interstellar medium. This process is incredibly efficient at moving and processing matter on a galactic scale. Over millions of years, a single active black hole can blow enormous bubbles of hot gas that rise above and below its galaxy, like those famously observed in the Perseus galaxy cluster. These structures are not temporary. They can persist for hundreds of millions of years, long after the jet itself has shut off, serving as a permanent monument to a past era of violent activity. We can see the evidence of this sculpting work through our most powerful X-ray telescopes, like the Chandra X-ray Observatory. Chandra's images are nothing short of breathtaking. They show galaxies and clusters not as serene islands of stars, but as dynamic systems etched with the intricate patterns left by these ancient jets. We see vast, ghostly bubbles filled with ultra-hot plasma, surrounded by brighter rims of compressed gas that were pushed outward by the jet's force. We see shock fronts, the precise edges where the jet's energy is slamming into the surrounding material, glowing intensely in X-ray light. These observations are like reading a history book written in hot gas. By analyzing the size, shape, and temperature of these structures, astronomers can work backwards. They can determine the power the jet must have had, how long it was active, and how much energy it injected into its surroundings. It's a form of cosmic forensics where the clues are these giant cavities and the echoes of shock waves. The metaphor of a sculptor shaping clay is perfectly apt here. The interstellar medium is the clay, largely formless and waiting. The astrophysical jet is the sculptor's hand, applying immense pressure and energy. Each stroke of the jet, each period of activity, leaves a permanent indentation, a ridge, or a hollow in the galactic material. Even when the sculptor's hand is withdrawn, the shape remains, telling any observer what happened there. This is memory in its most physical form. The distribution of matter in a galaxy cluster today is not random. It is the direct result of these powerful events that occurred in the deep past. The jets have literally rearranged the cosmic furniture, and that new arrangement is a durable record of their passage. The impact of these jets extends far beyond just creating interesting shapes. They play a crucial role in the life cycle of galaxies themselves, a process known as feedback. A supermassive black hole's jet acts as a powerful regulatory mechanism. By pumping enormous energy into the surrounding gas, the jet can heat it up so much that it prevents the gas from cooling down and collapsing to form new stars. In the most extreme cases, jets can even blow huge amounts of gas completely out of the galaxy, starving it of the raw material needed for future generations of stars. This means a dramatic event from 1 billion years ago, recorded in the form of jet-blown bubbles, directly dictates the current state of a galaxy, how many stars it has, how active it is, and even its shape. The memory of that violent outburst is not just stored, it is actively governing the present and future evolution of an entire galaxy. This transforms our view of these terrifying cosmic engines from mere destroyers to essential architects. They are key players in the story of cosmic structure, and their imprints are everywhere we look, from the vast radio lobes that stretch far beyond elliptical galaxies to the hotspots where jets terminate in a brilliant splash of radiation. The universe is filled with the lingering echoes of these tremendous outbursts. Each jet is a definitive entry in the universal ledger, an event so energetic that its signature is woven into the very distribution of matter and energy, ensuring that its story will be told for cosmic epochs to come. Moving beyond the violent outbursts of astrophysical jets, we find ourselves considering a far more subtle and ancient kind of cosmic inscription, one written not in hot gas but in the very geometry of spacetime. This brings us to one of the most fascinating and speculative ideas in all of cosmology, the concept of cosmic strings and other topological defects. Imagine the universe in its very first instance, a searingly hot and unimaginably dense soup where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were unified into a single, perfect symmetry. As this newborn cosmos expanded and cooled, it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. And just as freezing water can trap air bubbles or form cracks, the cooling universe might have trapped its own kind of imperfections in the fabric of reality. These are not made of matter, they are flaws in the structure of spacetime itself, and if they exist, they could be the ultimate time capsules, carrying information from the universe's first trillionth of a second. The most famous of these hypothetical relics is the cosmic string. Picture an incredibly thin, unimaginably dense filament of pure energy, a one-dimensional crack in spacetime left over from the early universe. Its properties are almost beyond belief. A cosmic string might be as thin as a proton but stretch across the entire observable universe, and just a single inch of it could weigh more than Mount Everest. This immense mass would warp the space around it tremendously, creating a gravitational lens so perfect that if one passed between us and a distant galaxy, we would see a double image of that galaxy, a perfect twin split by the string's incredible gravity. But its most astounding property is its durability. A true cosmic string, if formed, would be virtually indestructible, a stable relic that has survived unchanged for 13.8 billion years. It would be a fossil of a symmetry-breaking event, a permanent record of a specific moment when the laws of physics themselves changed, forever preserving a memory of that transition in its very existence. The pioneering work of theorists like Alexander Vilenkin and Tom Kibble has shown how these strings could do more than just exist. They could actively encode information. Vilenkin proposed that the network of strings formed in the early universe would not be static. These strings would oscillate wildly, and when two strings crossed, they could reconnect, or a string could loop back and pinch off into a closed ring. These dynamic processes are not random. They are dictated by the specific conditions of the universe's phase transition, the specific way the strings vibrate, the size of the loops they form, the density of the string network. All of these properties are a direct output of the physics of the universe's first moments. In this sense, a cosmic string is a timeline, a data stream frozen in spacetime geometry, waiting to be read. By studying the properties of a cosmic string, a physicist could theoretically work backwards to calculate the energy scale and the nature of the symmetry breaking that created it, accessing information that is otherwise completely inaccessible. To grasp how a defect can store historical data, think of the process of water freezing on a pond. The specific pattern of cracks that form in the ice doesn't happen by accident. It tells a detailed story about the conditions during the freeze, the temperature, the wind, any impurities in the water. All of these factors influence the pattern. By studying the cracks, you can deduce the history of the freezing event. Cosmic strings are the cracks in the ice of spacetime. Their distribution, their motion, and their very existence are a permanent testament to the specific conditions present during the cosmic phase transition that birthed them. They are not just relics, they are autographs from the universe's birth, signed in the language of gravity and geometry. The most exciting possibility is that we might not have to simply imagine these strings, we could actually detect them. An oscillating cosmic string or a collapsing loop would be a tremendous source of gravitational waves. Unlike the brief chirp from a black hole merger, a cosmic string would potentially produce a continuous, steady hum of gravitational radiation, a permanent background noise woven into the fabric of the cosmos. Our next-generation gravitational wave observatories, like the Laser Interferometer Space Antenna, or LISA, are being designed specifically to listen for this kind of primordial signal. Hearing that hum would be like tuning into a radio station that began broadcasting an infinitesimal fraction of a second after the Big Bang, providing direct, observational evidence for physics at energy scales a trillion times more powerful than anything we can create in our particle colliders. While cosmic strings are the most well-known example, they are part of a broader family of potential defects with equally exotic names: domain walls, magnetic monopoles, and textures. Each represents a different kind of knot in the fields that permeate the universe, formed under slightly different conditions during the early phase transitions. Their collective existence expands our notion of cosmic memory from something written on matter or in light to something embedded in the fundamental architecture of spacetime. It suggests that the universe's history might be recorded not just in what happened, but in how reality itself is structured, with flaws and wrinkles that tell a story billions of years old. The search for these topological defects is a search for the deepest and most permanent memories of all, a quest to read the original blueprint of existence from the cracks in its foundation. But perhaps the most profound implication of this observer-centric view is that we, as conscious beings, are not passive recipients of a pre-recorded cosmic history. We are active participants in its ongoing creation. Our act of observation, of questioning, and of measurement is the very process by which potentialities become actualities, by which the fog of quantum possibility condenses into the solid ground of experienced reality. In this sense, the universe's memory is not a static archive we merely access. It is a living story we are co-authoring with every experiment we conduct and every observation we make. The constants are fine-tuned not for life in general, but for observership, for the emergence of creatures capable of wondering about the tune and, in doing so, finishing the symphony. This transforms the anthropic principle from a mere selection effect into a profound statement about the interconnectedness of consciousness and cosmos, suggesting that the universe remembers itself into existence through us. Now, to truly grasp how deep the rabbit hole goes, we must shrink our perspective down to the most unimaginably tiny scales, to the very Planck length, where the smooth, predictable fabric of space-time we take for granted completely breaks down. At this fundamental level, the universe isn't a calm, continuous expanse. It is a seething, turbulent, and chaotic froth, a boiling ocean of pure potentiality known as quantum foam. This isn't a metaphor, it's a serious prediction of combining quantum mechanics with general relativity. Here, in this frenetic dance of existence, the concepts of here and there, and now and then lose all meaning. Space-time itself becomes uncertain, and this fundamental fuzziness might be the ultimate substrate for the universe's memory, written in the smallest possible script. The engine of this foam is the bizarre quantum phenomenon of vacuum fluctuation. We often think of a vacuum as pure, empty nothingness, but quantum physics tells us that even the utter void is alive with activity. Thanks to the Heisenberg uncertainty principle, which allows for brief violations of energy conservation, pairs of virtual particles, a particle and its antiparticle, are constantly and spontaneously flashing into existence everywhere throughout all of space. They borrow energy from the vacuum, exist for an infinitesimally short moment, and then annihilate each other, paying the energy back almost instantly. This isn't just theoretical. We can observe the effects of these fluctuations, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed together by the pressure of these virtual particles popping into being on the outside. The entire universe is perpetually shimmering with this ephemeral creation and destruction. So how could this chaotic, temporary process possibly store lasting information? The key is in the pattern. While each individual particle pair is fleeting, the overall behavior of the quantum foam is not random. The rate and nature of these fluctuations are dictated by the underlying geometry and energy density of spacetime at that specific point. A region of space with a strong gravitational field, like near a planet or a star, will have a different fluctuation profile than the empty void between galaxies. The vacuum itself has a state, and that state remembers the energy and matter that has shaped it. Every massive object that has ever existed, from a star to a human being, has subtly altered the quantum vacuum around it by its gravity, changing the statistical dance of virtual particles in its vicinity. That alteration is a permanent entry in the ledger, a tiny but non-zero change in the vacuum's memory that persists long after the object is gone. This idea of a structured vacuum leads us to one of the most ambitious theories in physics, loop quantum gravity. This framework, developed by theorists like Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, proposes a radical solution to uniting gravity with quantum mechanics. It suggests that spacetime is not continuous and infinitely divisible. Instead, it is woven from tiny, discrete, one-dimensional loops, a network of intersecting threads of space. Think of it as the universe's underlying pixelation, with each pixel being a Planck length in size. In this view, the smooth spacetime of our everyday experience is an illusion, much like a digital photograph appears smooth from a distance but is actually composed of individual pixels when you zoom in. These loops and their intersections can carry information, much like the bits in a computer. The quantum state of the universe could be described by the way these loops are connected and the quantum numbers associated with them, meaning the entire cosmic history is encoded in this evolving spin network. This brings us back full circle to the profound vision of John Wheeler, who not only gave us the term black hole but also championed the idea of geometrodynamics. Wheeler proposed that we shouldn't think of spacetime as a stage and matter as the actors upon it. Instead, he saw them as inseparable. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This is Einstein's general relativity. But Wheeler took it further, suggesting that the geometry of spacetime is the fundamental reality, and particles of matter are merely manifestations of that geometry, like knots or twists in the fabric. In his view, an electron might not be a point particle but a wormhole mouth, a topological feature of space itself. This intertwining of geometry and matter implies that information about every particle, every field, and every event is not in spacetime, it is spacetime. The memory of the universe is its shape, from the violent outbursts of galactic jets to the silent, statistical churn of the quantum foam. We see a universe that is inherently mnemonic. It is a cosmos that seems hardwired to record, to remember, and to tell its story through every possible medium, from light and gravity to the very structure of the vacuum. These aren't 10 separate, isolated mechanisms. They are interconnected layers of a single, profound truth. The universe is not a blank slate. It is a living, breathing archive, and every event, no matter how small or grand, contributes a verse to its ongoing epic. We are not just observers of this story. We are participants, our own lives and observations adding yet another layer of complexity to this magnificent, cosmic memory system. But beyond the violent churn of quantum foam and the geometric memory of spacetime, the universe is also filled with a far more tangible, yet utterly ghostly, form of historical residue, a ceaseless rain of ancient particles that have been streaming through everything since the dawn of time. We are talking about neutrinos, the universe's most elusive and abundant messengers. These subatomic phantomas are so reluctant to interact with normal matter that trillions of them are passing through your body every second, leaving absolutely no trace, as if you were a ghost to them and they to you. This very aloofness, this refusal to engage, is precisely what makes them such perfect cosmic archivists. Because they so rarely bump into anything, they can travel for billions of light years in a perfectly straight line, carrying information from their source completely unscathed and unaltered, delivering a pristine snapshot of the event that created them. The most ancient neutrinos of all form a sea that permeates all of space, a relic known as the cosmic neutrino background. If the cosmic microwave background is the universe's baby picture, taken 380,000 years after the Big Bang, then the cosmic neutrino background is its unimaginably earlier ultrasound, captured a mere 1 second after the initial singularity. At that moment, the universe was a seething plasma so dense that even neutrinos, which can pass through light years of lead, were briefly trapped. When the cosmos expanded and cooled enough for them to finally decouple and stream free, they did so, preserving a perfect fingerprint of the universe's condition at that 1 second mark. Detecting these particular neutrinos is one of the holy grails of cosmology, as they hold secrets about the very earliest moments of nucleosynthesis, the formation of the first atomic nuclei, and could provide an independent measure of the universe's expansion history that is completely free from the influence of later events. Detecting such faint, low-energy relics is a monumental challenge that will require technology we haven't yet invented, but we are already learning to read the messages carried by their higher energy descendants. Consider a colossal cosmic catastrophe like a supernova. For days before the star's visible light reaches its peak, it emits a tremendous burst of neutrinos. This is because neutrinos are produced in the furious nuclear reactions at the star's core and can escape the collapsing layers long before the shockwave breaks through the surface. This is exactly what happened with supernova 1987A. Hours before astronomers saw the light from the explosion, neutrino observatories on Earth detected a handful of these particles. They were the first messengers, the advance notice of a stellar death that had occurred 160,000 years ago. Those 24 detected particles carried more direct information about the core collapse process than all the light that followed. To catch these spectral messengers, we have built some of the most extraordinary detectors on, or rather in, the planet. Projects like the Ice Cube Neutrino Observatory at the South Pole use a cubic kilometer of deep, ancient Antarctic ice as a giant particle trap. Thousands of sensitive optical sensors are buried over a mile deep, waiting for the incredibly rare moment a high-energy neutrino does interact with an atom in the ice. When that happens, it creates a faint flash of blue light called Cherenkov radiation, which the sensors can trace back to pinpoint the neutrino's direction of origin. It's astronomy, but not with light. It's like building a telescope that sees in neutrino vision, allowing us to peer directly into the hearts of the most energetic and obscured objects in the universe, like active galactic nuclei and gamma-ray bursts, whose visible light is often hidden behind walls of cosmic dust. The power of neutrinos as memory-keeping devices can be understood through a powerful analogy. Imagine a great library is on fire. The books written on parchment and paper are consumed by the flames, their information lost forever. But a few scrolls written on indestructible, fireproof clay tablets survive the inferno completely unchanged. While the fire scrambles and destroys the information on the paper, the information on the clay tablets remains perfectly preserved. In the cosmic context, the violent chaos of a supernova or a black hole accretion disk is the fire. Photons of light are like the paper books. They interact strongly with the hot, turbulent plasma and magnetic fields, getting scattered, absorbed, and their information scrambled before they finally escape. But neutrinos are the clay tablets. Their weak interaction means they fly straight out of the heart of the inferno, their energy and direction untouched, carrying a clean, unambiguous signal from the event's epicenter. They are the ultimate durable record, surviving cosmic fires that would obliterate any other form of information. This makes the study of neutrinos, from the relic background to those from modern cataclysms, absolutely vital to our understanding of cosmic history. They provide a complementary channel of information to light and gravitational waves, one that is often more direct and less corrupted. By combining all these different messengers, light for chemical composition, gravitational waves for mass and dynamics, and neutrinos for internal nuclear processes, we are entering the era of multi-messenger astronomy. This allows us to cross-check the universe's story, to read the same event through different, independent memory systems, and build a far more robust and trustworthy history of everything. Each high-energy neutrino detected is a time-stamped postcard from a distant, violent event, and the faint, ancient sea of relic neutrinos is the foundational parchment upon which the earliest chapters of the universal story were first written. While neutrinos offer a ghostly whisper from the most violent events, the very stars that light up the night sky provide a far more visible and enduring chronicle of cosmic history. This is the field of galactic archaeology, where astronomers act as cosmic genealogists, using the light from ancient stars to read the autobiography of our galaxy, and by extension, the entire universe. Every star is more than just a beacon of light. It is a fossil, a chemical time capsule that preserves within its atmosphere the elemental ingredients present in the cloud of gas from which it was born. By carefully analyzing the spectrum of a star, the unique fingerprint of light that reveals which elements are present and in what quantities, we can determine not only its age but also the history of the cosmic environment that created it. The story begins with the first generation of stars, known as Population 3 stars. These titans are thought to have been immense, short-lived behemoths composed almost entirely of hydrogen and helium, the only elements forged in the Big Bang. They lived fast and died young, ending their lives in spectacular supernova that for the first time seeded the pristine cosmos with heavier elements like carbon, oxygen, and iron. The next generation of stars, population 2, formed from this now enriched gas. They contain smaller but measurable amounts of these heavier elements, which astronomers collectively call metals. By finding and studying these ancient metal-poor stars, some of which are nearly as old as the universe itself, we are effectively reading the last will and testament of those first, long-vanished stellar giants. Their chemical composition is a direct record of the nucleosynthesis, the element building, that occurred in the earliest generations. This process is beautifully analogous to a genealogical DNA test. When you send a sample to a company, they don't just tell you about you, they trace your unique genetic markers back through time, revealing your ancestry, the migration patterns of your ancestors, and even potential relatives you never knew you had. A stellar spectrum does the exact same thing on a cosmic scale. The specific ratios of elements in a star's atmosphere are its unique genetic code. A high ratio of europium to iron, for example, points to an ancestry seeded by a specific type of supernova. By mapping the chemical DNA of hundreds of thousands of stars, we can reconstruct the family tree of the Milky Way, identifying stellar siblings that formed from the same ancient gas cloud long since dispersed, and tracing their journeys across the galaxy. To conduct this massive project of cosmic genealogy, we need a map, a precise, three-dimensional chart of the positions and motions of over 1 billion stars. This is the monumental achievement of the European Space Agency's Gaia mission. Since its launch, Gaia has been tirelessly observing the sky, measuring the parallax, proper motion, and velocity of stars with breathtaking precision. It is essentially creating the first ever motion picture of our galaxy, allowing us to not only see where stars are now, but to rewind the clock and see where they came from. This dynamic map has revealed that the Milky Way is not a serene, stable spiral. It is a living entity still vibrating from past traumatic encounters. The most dramatic of these encounters are galactic mergers. When a small galaxy is devoured by a larger one like our Milky Way, it doesn't just vanish. It leaves behind indelible forensic evidence. The gravitational pull of the merger tears the victim apart, stretching its stars into vast, faint rivers of light that stream across the halo of the host galaxy. These stellar streams, as they're called, are the cosmic equivalent of a bloodstained pattern at a crime scene, allowing us to reconstruct the event long after it happened. Gaia's data has been instrumental in discovering dozens of these streams, the ghosts of long-dead dwarf galaxies whose stars are now irrevocably woven into the fabric of our own. Furthermore, the dark matter halo that once surrounded the devoured galaxy also leaves a gravitational imprint, a subtle disturbance in the motions of stars that can be traced back to the merger, proving that even the invisible components of the universe leave a lasting record. Surveys like Gaia and the ground-based Sloan Digital Sky Survey are thus building a living library of cosmic evolution. Each star is a volume in this library, and its light signature is the text on the page, telling us when it was written and what was happening in the universe at that time. By cross-referencing a star's chemical DNA with its orbital dynamics from Gaia, we can place it in its proper historical context. We can identify stars that are true natives of the Milky Way's thick disk and others that are immigrants from foreign galaxies, assimilated billions of years ago. This allows us to piece together a timeline of our galaxy's growth, from its initial collapse from a primordial gas cloud to its steady accretion of smaller neighbors, building itself up over cosmic time. The grand structure of the galaxy itself, from its spiral arms to its central bulge, is therefore not just a beautiful arrangement. It is a physical archive, a monument to the cumulative events of the past 13 billion years, with every star serving as a keeper of a specific chapter in that grand, ongoing story. Now let's turn our attention to a force so fundamental it shapes reality at every scale, yet remains completely invisible to our eyes: magnetism. We often think of magnetic fields as temporary phenomena, the kind that fade when you turn off an electromagnet or lose a refrigerator magnet. But across the cosmos, magnetic fields achieve something astonishing. They become permanent, fossilized records, etching the history of cosmic events into space itself with incredible durability. These aren't fleeting forces, they are the universe's magnetic tape, recording and preserving information for billions of years. The story of cosmic magnetic memory begins with a process called a dynamo. Much like the dynamo on a bicycle that uses rotational motion to generate light, cosmic dynamos convert kinetic energy, the motion of conductive fluids, into magnetic energy. Inside a star like our Sun, the churning of superheated plasma acts as a massive dynamo, generating a complex magnetic field that drives sunspots and solar flares. On a far grander scale, the spiral arms of a galaxy are filled with ionized gas and cosmic rays, and as the galaxy rotates, this conductive material can generate a galactic-scale magnetic field. These fields aren't confined to stars or galaxies. They can stretch across entire galaxy clusters, weaving through the vast spaces between galaxies, where they are amplified and shaped by the violent motions of colliding gas and entire galaxies during cluster mergers. Perhaps the most relatable example of magnetic memory is right beneath our feet. Certain types of rocks, particularly volcanic rocks like basalt, contain tiny minerals such as magnetite. When these rocks are molten, these mineral grains are free to move. As the rock cools and solidifies, these grains align themselves with the Earth's magnetic field at that exact moment in time, locking that magnetic orientation into the stone forever. Geologists studying these paleomagnetic records have discovered something extraordinary. Our planet's magnetic field has completely reversed its polarity numerous times throughout history. These rocks are not just stones, they are chapters in Earth's diary, recording every flip of the magnetic poles over hundreds of millions of years. This proves that magnetic fields can serve as a highly durable storage medium. This principle of magnetic fossilization extends magnificently to cosmic scales. When galaxies collide within a cluster, the process is not gentle. It's a turbulent, violent event that shocks and compresses the gas between galaxies. This turbulence can stretch, fold, and amplify pre-existing magnetic fields, much like a baker kneading dough layers iron filings into a consistent pattern. The resulting magnetic field structures, often taking the form of vast, ordered filaments that follow the contours of ancient shock waves, become a permanent imprint of that merger event. Long after the galaxies have passed through each other and the visible evidence of the collision has faded, the magnetic fossil remains, preserving a memory of the encounter's dynamics, direction, and energy. But how do we, who cannot see magnetic fields, possibly detect these cosmic imprints? We listen to the music they create. When high-energy electrons, often accelerated by shock waves from supernova or galactic collisions, spiral along these magnetic field lines, they emit a very specific type of radiation called synchrotron radiation. This emission is most prominent in the radio part of the electromagnetic spectrum. Our giant radio telescopes, like the Very Large Array in New Mexico or the upcoming Square Kilometer Array, are essentially tuned to hear this cosmic radio symphony. The polarization and intensity of this synchrotron radiation allow astronomers to map the invisible magnetic structures in exquisite detail. By reading this radiation, we can trace the strength and orientation of magnetic fields across millions of light years, effectively developing a form of cosmic magnetic resonance imaging, or MRI, for the universe. A powerful way to conceptualize this is to think of old-fashioned magnetic tape, the kind used in cassette recorders. The tape itself is just a strip of plastic coated with a magnetic material. But when it moves past the record head, an electrical signal representing sound, a concert, a voice, a moment in time is translated into a pattern of magnetization on the tape. To retrieve the memory, you simply play the tape back. Cosmic magnetic fields operate on a similar principle. The energetic event, a galaxy merger, a quasar outburst, a supernova blast wave provides the electrical signal. The conductive plasma permeating space acts as the tape, and the magnetic field pattern that is frozen into that plasma becomes the stored memory. The synchrotron radiation we detect is the universe playing that tape back for us, allowing us to hear the echoes of cosmic events that occurred in the deep past. This transforms our understanding of the empty space between stars and galaxies. It is not a true void, it is a vast magnetized medium crisscrossed with the fossilized remnants of ancient violence. These magnetic fossils don't just tell us that an event happened, they reveal the specific mechanics of how it happened. The intricate patterns can indicate the direction of a galactic collision, the strength of a shock wave from a supernova remnant, or the powerful outflow from a central black hole. In this way, magnetism provides a unique and robust layer of the universe's memory system, a physical medium that captures the dynamics of cosmic history and preserves it across eons, waiting for us to develop the tools to decode its timeless recordings. But if magnetic fields act as a kind of cosmic tape recorder, we must now confront the fundamental force that governs all recording and erasure, the very engine of change itself, entropy. This concept, often simplified as a measure of disorder, is deeply intertwined with the arrow of time and is arguably the most critical prerequisite for any form of memory to exist at all. To understand why, we have to go back to the 19th century and the work of Ludwig Boltzmann, a physicist who made the startling connection between the microscopic world of atoms and the macroscopic world of our experience. He realized that entropy is not about disorder in a messy room sense, it's about probability. A high entropy state is simply a highly probable arrangement of particles, while a low entropy state is a very specific and therefore improbable arrangement. This statistical view leads to a profound insight about memory. Think of an egg falling from a counter and smashing on the floor. We all know the video of that event would look ridiculous if played in reverse. Eggs do not spontaneously reassemble themselves and leap back onto the counter. The broken egg is a high entropy state. There are countless ways for the shell and the yolk to be scattered. The intact egg is a very specific, low entropy state. Our ability to remember the event of the egg falling, and indeed our very perception of time moving forward, depends entirely on this transition from a low probability state to a high probability one. If the universe were in a state of maximum entropy, a featureless equilibrium where nothing ever changes, no events could occur, and thus there would be nothing to remember. Memory requires a universe that is out of balance, with a clear gradient from a low entropy past to a high entropy future. This gradient is the arrow of time, and it is the canvas upon which all cosmic memories are painted. Boltzmann himself speculated on this connection, suggesting that a memory in our brain is essentially a stable, low-entropy configuration of neurons that was created by a past event. The persistence of that specific configuration is a record of what happened. But for that record to form, the universe had to have been in an even lower entropy state in the more distant past to allow for the event to create the configuration in the first place. This chain stretches all the way back to the initial, incredibly low entropy state of the Big Bang. The entire history of the universe and our ability to reconstruct it hinges on that single, improbable starting condition. Modern physicists like Seth Lloyd have pushed this idea even further, framing the entire universe not just as a physical system, but as a giant information processing system. Lloyd connects information processing directly to the laws of thermodynamics. Every time a bit of information is processed, whether in a computer, a brain, or a star, it requires energy and produces a tiny amount of waste heat, increasing the entropy of the surroundings. In this view, the act of remembering itself is a thermodynamic process. To record an event, you must expend energy to create a specific, low-entropy order, and in doing so, you inevitably increase the total entropy of the universe elsewhere. The cosmic memory bank is built and maintained at the cost of the universe's overall trend toward disorder. A powerful metaphor for this is a deck of cards. A brand new deck, fresh out of the box, is arranged in perfect sequential order by suit, a very specific low-entropy state. When you shuffle that deck, you randomize it, increasing its entropy. But here's the crucial point. The specific sequence of cards after the shuffle is not random from an informational standpoint. It is a direct, detailed record of the exact shuffling process it underwent. If you could know the initial order and the precise mechanics of the shuffle, you could work backwards to determine the entire history of how the deck arrived at its current state. The high entropy result still contains a perfect memory of the process that created it. The information is preserved, just in a more scrambled form. The universe is like that shuffled deck. The increase in entropy doesn't destroy information. It transforms it and makes it harder to read, but the history is still there, encoded in the present arrangement of everything. This reshapes our understanding of the universe's ultimate fate. The heat death, the state of maximum entropy, is not a state of erased information, but one of maximally scrambled information. The history of every event that ever occurred would still, in principle, be preserved in the microscopic configuration of all the particles in the universe. However, that information would be so diffuse, so chaotic, and so lacking in any coherent patterns that it would be effectively lost to any conceivable observer. The cosmic ledger would still exist, but it would be written in a language with no grammar, a single, uniform, and timeless state where the past and present are indistinguishable. This deep connection between entropy, information, and time reveals that the universe's ability to remember is not a separate feature but a direct consequence of its journey from a unique beginning toward an uncertain future, a journey powered by the relentless and creative force of increasing disorder. Now we arrive at perhaps the most speculative and imagination-stretching possibility of all, a concept that pushes the very boundaries of how memory might operate, not just across space but across time itself. We are venturing into the realm of wormholes and closed time-like curves, theoretical constructs within Einstein's general relativity that suggest information might not only be stored, but could potentially travel backwards, creating a form of cosmic memory that loops and intertwines with itself. The most famous of these hypothetical structures is the Einstein-Rosen bridge, more popularly known as a wormhole. Picture the universe not as a flat sheet, but as a three-dimensional volume. A wormhole would be a tunnel or a shortcut connecting two distant points in this volume, like a cosmic subway line burrowing through the Earth instead of traveling the long way around the surface. In principle, such a tunnel could connect not just different places, but different times, creating a bridge between the past and the future. The idea of a wormhole preserving information is a powerful one. Imagine an event of immense importance, a message meant for a civilization 1,000,000 years in the future. Instead of broadcasting it into space where it would fade and disperse, you could, in theory, encode that information, and send it directly into a stable wormhole whose other end opens in that distant future. The information wouldn't just be stored passively, it would be actively transmitted across epochs, arriving perfectly intact as if no time had passed at all. The wormhole would act as the ultimate time capsule, but unlike one buried in the ground, this capsule is connected by a tunnel through the very fabric of reality, ensuring its contents are delivered directly to the intended recipient in another age. But there is a monumental catch, a reason why this remains in the domain of speculative physics. According to our best models, a wormhole capable of allowing such passage would be incredibly unstable. The immense gravitational forces involved would cause it to collapse into a singularity faster than any information could travel through it. The only hypothetical way to prop it open, to make it traversable, would be to thread it with something known as exotic matter. This isn't antimatter, it's a theoretical substance that possesses negative energy density or negative pressure, effectively generating a kind of anti-gravity that could counteract the wormhole's tendency to pinch off. While quantum mechanics allows for the existence of tiny amounts of negative energy in certain circumstances, whether enough could ever be gathered and manipulated to stabilize a macroscopic wormhole is a question that lies far beyond our current technological or theoretical horizon. This leads us directly into the heart of one of the most famous puzzles in all of science fiction and philosophy, the Grandfather Paradox. If a wormhole could allow you to travel back in time, what would stop you from accidentally preventing your own grandfather from meeting your grandmother, thereby preventing your own birth and creating a logical contradiction? This paradox seems to make time travel an impossible fantasy, a violation of cause and effect that would unravel reality itself. However, some physicists, like Igor Dmitrievich Novikov, have proposed a possible way out through what's called the self-consistency principle. Novikov suggested that the laws of physics simply will not allow paradoxes to occur. Any actions taken by a time traveler would already be a part of history, and they would find themselves compelled to act in a way that is perfectly consistent with the established past. You might travel back in time with the intention of changing history, but you would inevitably become the very reason events unfolded the way they did, your actions seamlessly woven into the timeline without any contradiction. Quantum mechanics offers another fascinating resolution through the many worlds interpretation. In this view, a time traveler entering a wormhole to the past wouldn't arrive in their own history, but would instead branch off into a new, parallel universe that is nearly identical up to the moment of their arrival. Any actions they take, including problematic ones like interfering with their ancestry, would affect only that new timeline, leaving their original history completely untouched and paradox-free. The information hasn't been erased or changed. It has simply been shared or transferred to a new branch of the multiverse, expanding the cosmic memory system into a vast, branching tree of possibilities. The most profound implication of all this is the potential for a universe that is fundamentally self-referential. If closed time-like curves, paths through space-time that loop back on themselves, are possible, then information could exist in a state of causal loops. A piece of information would have no true point of origin. It would simply exist forever circulating through time, its own cause and its own effect. It would be a memory with no beginning, a story that the universe tells itself for all eternity. While these ideas stretch our comprehension to the breaking point, they force us to consider that the universe's memory might not be a linear record of a finished past, but a dynamic, interconnected web where past, present, and future are fundamentally linked in a way we are only beginning to imagine. But what if the cosmic ledger we've been exploring isn't confined to a single volume? What if our universe, with all its intricate mechanisms for storing memory, is just one book in an infinite library, each volume telling a different version of reality. This brings us to perhaps the most expansive and mind-bending possibility of all, the concept of the multiverse, a cosmic ensemble where memory is not just preserved within a universe, but across countless parallel realities, each with its own unique history and physical laws. The idea that our cosmos might be part of a much vaster multiverse isn't just science fiction. It emerges naturally from several of our most successful scientific theories, suggesting that the totality of existence might be an archive of literally everything that can possibly happen. One of the strongest scientific arguments for a multiverse comes from a refined version of the theory of cosmic inflation, the idea that the universe underwent a period of exponential expansion in its first moments. The theory of eternal inflation proposes that this inflationary process never truly stopped everywhere. Instead, it suggests that the rapid expansion of space-time is like a boiling pot of water that never stops bubbling. In most regions, inflation ends, allowing a stable universe like ours to form. These are the bubbles in the froth. But in between these bubbles, the inflationary process continues at an incredible rate, constantly creating new space-time and spawning new bubble universes. Each of these bubbles would have its own unique properties, a random selection of physical constants and laws determined by how inflation ended in that particular region. In this view, every possible universe that can form does form. Each bubble is a self-contained cosmos, preserving a perfect and permanent record of its own specific inflationary seed event, a unique entry in the multiverse's infinite catalog. String theory, a leading candidate for a theory of everything, adds another layer of breathtaking depth to this idea with its concept of the landscape. The theory requires extra spatial dimensions beyond the three we experience, which are thought to be curled up or compactified in an enormous number of different ways. Each possible way of curling up these dimensions results in a universe with a different vacuum state, a universe with different fundamental constants, different particles, and different forces. The number of these possible configurations is staggeringly vast, often estimated to be around 10 to the 500 power. Each of these possible universes within the string theory landscape represents a different, stable solution, a different page in the cosmic manual of physics. The information about how those dimensions are compactified is permanently baked into the laws of that universe, making each one a frozen memory of a specific mathematical possibility. Our universe, with its specific constants that allow for stars, planets, and life, would be just one point in this incomprehensibly vast landscape. To wrap our minds around this, imagine the ultimate library. This isn't a library with millions or even billions of books. It is a truly infinite library containing every book that has ever been written, every book that could ever be written, and every possible variation of every book. In one volume, you might read a history of the world where the dinosaurs never went extinct. On another shelf, you find a biography of yourself, but in a reality where you made a different choice at a pivotal moment. Some books are written in languages you can't comprehend, their scripts based on different physics. This library is the multiverse. Each universe is one of these books, and its entire history, from its inflationary beginning to its final heat, death, or big crunch, is the story written on its pages. The memory of every possible event is stored not within a single universe, but across the entire collection. Nothing is forgotten because every possibility exists somewhere in the stacks. This radically expands our understanding of cosmic memory. It's no longer just about tracing the residue of events within our single space-time continuum. It becomes about the preservation of possibility itself. A historical event in our world, like the outcome of a specific war or the extinction of a species, is just one version of that event. The multiverse hypothesis suggests that every alternative outcome is equally real, playing out in its own separate volume of reality. The cosmic memory bank is therefore not just recording what did happen, but also what could have happened. This doesn't devalue the memories within our universe. Instead, it frames them as one thread in a grand, hyper-dimensional tapestry of existence, where the complete story of everything is the sum of all possible stories across the infinite multiverse. But how does the fragile, probabilistic world of quantum possibilities ever resolve into the solid, objective reality we all seem to share? If a quantum system exists in a blur of multiple states until it is observed, why do different observers consistently agree on what they see? The answer to this profound question may be one of the most elegant and universal memory mechanisms of all, a process known as quantum Darwinism. This theory, pioneered by physicist Cyclical, proposes that the universe itself is constantly performing measurements, and in doing so, it is redundantly writing the history of events into the very environment around us. The transition from quantum weirdness to classical certainty isn't a mysterious collapse. It's a form of cosmic broadcasting, where information is copied and spread until it becomes public knowledge. At the heart of quantum theory is the concept of superposition, the idea that a particle can exist in multiple states or locations simultaneously. This fragile state is easily disrupted by any interaction with its surroundings, a process called decoherence. But quantum Darwinism reveals that decoherence isn't just a destructive force that wipes out quantum magic. It is a creative and selective process. When a quantum object interacts with its environment, be it a shower of photons, a mist of air molecules, or even the cosmic microwave background radiation, it doesn't just randomly collapse. It imprints information about its specific state onto those environmental particles. A single photon bouncing off a molecule doesn't just change direction. It carries away a tiny piece of data about that molecule's position, its charge, or its magnetic field. This happens not just once, but trillions upon trillions of times, as countless environmental particles constantly bombard every object. This is where the Darwinism comes in. The environment isn't just recording information, it is selectively proliferating the most stable, robust information. Think of it as a form of natural selection for quantum states. A fragile, unstable quantum state will be quickly scrambled and lost by decoherence, but a state that is resilient will have its information copied over and over again into the environment. These countless copies are made and scattered into the surrounding space, creating a redundant, durable record. This is why we perceive an objective reality. You and I don't need to directly measure a subatomic particle to agree on its properties. Instead, we both simply access the same, widely available environmental record. We are both reading from the same cosmic bulletin board that has been plastered with identical flyers. A perfect example is the simple act of seeing. You look at a coffee cup on your desk. You are not directly interacting with the cup itself. You are catching the photons of light that have scattered off its surface. Each one of those photons has been imprinted with information about the cup, its shape, its color, its location. Your eyes and brain are not causing the cup to exist. They are simply gathering the copies of information about the cup that have been redundantly encoded into the photon environment by countless previous interactions. The cup's location isn't a secret. It's public information broadcast for anyone with the right receiver to detect. This process can be beautifully understood through the analogy of gossip spreading through a small town. Imagine a single, secret event happens. Perhaps two people share a kiss at a secluded park. That initial event is like a fragile quantum state, known only to the two participants. But if a third person glimpses them, that person becomes an environmental particle that carries the information away. They tell one friend who tells another, and soon the story is being repeated at the grocery store, the coffee shop, and the town hall. The information about the kiss has been redundantly encoded into the social environment of the town. It is no longer a secret known to a few. It has become objective, agreed upon reality for the entire community. Anyone can access this truth simply by asking around. They are all sampling the same widely distributed environmental record. Quantum Darwinism elegantly bridges the gap between the quantum and classical worlds, but its implications stretch far beyond explaining our everyday reality. It suggests that the environment is not a passive backdrop but an active participant in the universe's information storage system. The space around every object, from a dust mote to a distant galaxy, is teeming with these redundant information copies. The light echoing through interstellar space, the cosmic rays zipping through galaxy clusters, the neutrinos streaming from the sun, all of them are carriers of this environmentally encoded data. They form a pervasive, low-volume hum of information, a constant recording of the state of everything they have ever interacted with. In this view, the entire cosmos is engaged in a never-ending process of observation and communication, with every interaction adding another line to the indelible, distributed ledger of cosmic events, ensuring that what happens is never truly lost but is instead woven into the very fabric of the environment for all time. To understand how the entire cosmic memory system could even begin, we must rewind the clock to the most unimaginably brief moment after the Big Bang, to an event of such monumental power that it literally set the stage for everything to come. This is the epoch of cosmic inflation, a concept that solves several major puzzles in cosmology and, most importantly for our story, provides the very first entries in the universe's ledger. For a fraction of a second so tiny it defies comprehension, around 10 to the negative 36 seconds, the universe didn't just expand, it underwent a hyper-exponential growth spurt, inflating by a factor of at least 10 to the 78 in volume. This wasn't a gentle unfolding, it was a violent stretching that took a region of space smaller than a subatomic particle and blew it up to something larger than our entire observable universe today. This explosive event didn't just create space, it also created the initial conditions, the primordial seeds, from which all cosmic memory would eventually grow. The magic of inflation lies in its ability to transform the utterly random and chaotic quantum world into something large, stable, and permanent. In the seething quantum foam that characterized the pre-inflationary universe, virtual particles were constantly flickering in and out of existence due to the Heisenberg uncertainty principle. These were quantum fluctuations, tiny, temporary wrinkles in the fabric of spacetime itself. Under normal circumstances, these fluctuations would appear and vanish far too quickly to have any lasting effect. But inflation acted like a cosmic camera with an incredibly fast shutter speed. It captured these fleeting quantum ripples, and as space expanded at a speed faster than light, it stretched them across the entire cosmos. In a breathtakingly short time, these microscopic quantum wrinkles were magnified to astronomical sizes, frozen into the very geometry of the universe as macroscopic variations in density. The universe went from a chaotic quantum mess to having a very specific, slightly lumpy blueprint. A simple but powerful metaphor helps illustrate this incredible process. Imagine taking a perfectly smooth balloon and using a sharp pencil to draw a few tiny, almost imperceptible dots and squiggles on its surface. Now start inflating the balloon. As it expands, those minuscule marks don't just get bigger, they become major features. A tiny dot becomes a large continent. A faint squiggle stretches into a massive mountain range. The act of inflation doesn't create new features. It takes the tiny, random imperfections that were already there and magnifies them, making them permanent and defining the entire large-scale structure of the balloon's surface. Cosmic inflation did exactly this. The random quantum fluctuations were the tiny pencil marks on the uninflated universe. The inflationary expansion was the breath that blew up the balloon, stretching those quantum seeds into the vast cosmic web of galaxies and voids we see today. The evidence for this magnificent story is written across the sky in the oldest light we can see, the cosmic microwave background radiation. The incredibly precise temperature map of the CMB, produced by missions like Planck, is not a featureless, uniform glow. It is a detailed tapestry of hot and cold spots, variations of mere millionths of a degree. These spots are not random noise. They are the direct imprint, the fossilized echo, of those primordial density variations that inflation created. The specific statistical pattern of these hot and cold spots, how many are a certain size, how they are correlated with each other, acts like a fingerprint. It tells us definitively that the seeds for all structure were laid down by quantum fluctuations that were stretched and frozen by inflation. The Planck data didn't just confirm inflation happened, it strongly supports specific models of it, revealing details about the energy scale and the precise dynamics of the inflationary field that drove this explosive expansion. We are essentially reading the physics of the universe's first trillionth of a second from a baby picture taken 380,000 years later. This process establishes the most fundamental layer of the universe's memory system. The pattern of galaxies, clusters, and superclusters is not arbitrary. The location of every single star, including our own sun, and every planet, can ultimately be traced back to the specific pattern of those quantum fluctuations that were amplified during inflation. The universe remembers its own quantum origin story. The slightly denser regions in that initial blueprint, gifted a tiny gravitational head start, spent the next 13.8 billion years pulling in more and more matter, eventually collapsing into the glittering cities of stars we call galaxies. The less dense regions became the vast, empty cosmic voids. In this way, the largest structures in the cosmos are direct, living descendants of the smallest possible quantum events. The memory of that initial moment is not stored in one place. It is the architecture of the observable universe itself. Inflation provided the canvas and the first brushstrokes, and every event that followed, every supernova, every galactic collision, every birth of a star has been adding another layer of detail to this magnificent, ever-evolving cosmic memoir. But to truly grasp the most radical reimagining of where and how the universe keeps its records, we must venture into one of the most mind-bending concepts in all of theoretical physics. This is the holographic principle, an idea so profound that it suggests everything we perceive in our three-dimensional reality, every galaxy, every planet, every one of us might actually be a projection of information stored on a distant, two-dimensional surface. It's a theory that fundamentally redefines the nature of memory itself, proposing that the cosmos doesn't store its history within its volume, but on its boundary, like a cosmic credit card hologram encoding a three-dimensional image on a flat, two-dimensional strip. The seeds of this revolutionary idea were planted not in the study of the cosmos at large, but in the enigmatic thermodynamics of black holes. Physicists Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its information content, is not proportional to its volume as one might intuitively expect. Instead, it is directly proportional to the surface area of its event horizon. This was a staggering revelation. It implied that all the information describing everything that had ever fallen into a black hole was somehow encoded on its two-dimensional spherical surface. The three-dimensional interior, with its crushing singularity, was somehow an illusion. The true reality, the complete data set, was on the boundary. This discovery forced physicists to ask a breathtaking question. If this is true for a black hole, could it be true for the entire universe? Could our vast three-dimensional cosmos, with its billions of galaxies, actually be a holographic projection from a two-dimensional surface at the edge of everything we can see? This is not mere speculation. It found its most powerful expression in the work of physicist Juan Maldacena, who in 1997 proposed a concrete mathematical framework for this holographic universe. His discovery is known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. In essence, Maldacena provided a precise dictionary for translating between two completely different worlds. On one side, you have a universe with gravity, described by string theory operating in a warped, higher-dimensional space. On the other side, you have a quantum field theory without gravity at all, operating on the lower-dimensional boundary of that space. The mind-blowing implication is that these two descriptions are physically equivalent. A complex calculation involving gravity and strings in the bulk of the universe is exactly the same as a different calculation involving quantum particles on its boundary. The boundary theory, living in one less dimension, contains all the same information as the full-dimensional universe it surrounds. The engine that makes this holographic encoding possible is the very phenomenon we explored earlier, quantum entanglement. The countless threads of entanglement that weave together particles on the boundary are what generate the geometry of the space within. It's as if the fabric of space-time itself is knitted together by these quantum correlations. A highly entangled boundary corresponds to a smooth, continuous space in the bulk. A disruption or reduction in that entanglement would manifest as a tear or a singularity in the fabric of reality. In this view, the three-dimensional world we experience isn't the fundamental reality. It is an emergent property, a projection of the complex, entangled information stored on the two-dimensional surface at the edge of the cosmos. Our perception of depth and volume is a magnificent illusion. A powerful analogy to understand this is indeed the hologram on a credit card. That shimmering, three-dimensional image of an eagle or a globe isn't actually three-dimensional. It is a flat, two-dimensional surface that has been expertly etched with microscopic patterns. When light strikes these patterns, it diffracts in such a way that our eyes and brain reconstruct a convincing image with depth and parallax. The information for the entire three-dimensional appearance is compressed onto a two-dimensional plane. The holographic principle suggests the universe operates on a similar, albeit infinitely more complex, principle. The entire history of every event, the position of every particle, the memory of every supernova, all of it is encoded on the vast two-dimensional boundary of the observable universe. What we experience as the flow of time and the expanse of space is simply that data being read out and projected into the volume. This transforms our understanding of cosmic memory in the most fundamental way. It means that when we look up at the night sky, we are not looking out into a storage vault of events. We are, in a sense, looking at the storage medium itself. The boundary of the universe is the ultimate hard drive, and the events within it are the data being processed. A gravitational wave passing through Earth is not just a ripple in space, it is a change in the information encoded on the boundary. The light from a distant quasar is not just a photon traveling through emptiness, it is part of the projection. This principle offers a stunningly elegant solution to the black hole information paradox, suggesting the information never actually falls into the three-dimensional hole. It is always and forever encoded on its two-dimensional surface, preserved perfectly even as the black hole evaporates. The holographic principle is more than just a wild idea. It is a radical shift in perspective that places information at the very foundation of physical reality. It proposes that the universe is not made of space and time, but of bits and correlations. The cosmos is not a container of memories. It is a memory system itself, a dynamic hologram projecting its own past, present, and future from the infinite data bank of its boundary. But if the holographic principle suggests our reality is a projected image, a profound question remains: what or who is the projector? This leads us to one of the most contentious and fascinating debates in all of physics, a question that sits at the strange intersection of quantum mechanics, philosophy, and neuroscience. What is the role of consciousness itself in shaping reality, and by extension, activating the cosmic memory? For decades, a minority interpretation of quantum mechanics has proposed a truly radical idea: that the conscious act of observation is not a passive recording of events, but the very mechanism that makes events real in the first place. This perspective is most famously associated with the von Neumann-Wigner interpretation, named after the brilliant mathematicians John von Neumann and Eugene Wigner. In the standard formulation of quantum mechanics, a particle exists in a blurry cloud of probabilities, a superposition of many possible states until it is measured. The mathematics describes this transition with the so-called collapse of the wave function, but it is notoriously silent on what exactly constitutes a measurement. A rock, a camera, a cat. Von Neumann argued that the entire chain of measurement devices from a Geiger counter to a computer screen could themselves be described by quantum mechanics and would therefore simply become part of the larger superposition. He concluded that the only thing that could not be described quantum mechanically, the only thing that could break the chain and definitively collapse the possibilities into a single actuality, was the immaterial phenomenon of conscious awareness. In this view, the universe remains a realm of pure potentiality until a conscious mind looks at it, forcing it to make a choice and inscribe that result into the permanent record. To grasp how bizarre this implication is, consider the classic Schrödinger's cat thought experiment. The cat in the box is simultaneously alive and dead until someone opens the lid and looks inside. According to the von Neumann-Wigner view, it is not the triggering of the poison vial or the Geiger counter that resolves the situation. It is the conscious observation of the scientist that finally crystallizes one historical timeline, a timeline where the cat is definitively alive or definitively dead, and all the information associated with that outcome instantly becomes part of the universe. Memory, the conscious observer, acts as the ultimate arbiter of reality, the final judge that renders a verdict on what actually happened. This idea finds even more startling support in modern variations of the double-slit experiment, particularly the quantum eraser. In these experiments, physicists can seemingly change the past behavior of a particle based on a measurement choice made in the present. A photon can appear to have traveled through the apparatus as a particle or a wave, and which history it seems to have followed can be determined by an experimenter's decision after the photon has already been detected. It's as if the universe is waiting for a conscious observer to choose how to look at the data before it decides what actually occurred way back when. The past isn't a fixed, written record. It's more like a draft, with the final version only being committed to the cosmic ledger upon conscious inspection. A powerful metaphor for this is a photograph taken with a special type of film that only develops when someone looks at it. The event happens, light strikes the film, but the image remains latent, a swirl of unrealized possibilities. Countless potential images are all vying to exist. It is only when a conscious observer turns their gaze upon it that one specific image snaps into sharp focus, forever fixing that moment in time. In this analogy, the entire universe is like that photographic film, with conscious beings acting as the developers, bringing definite events into existence simply by perceiving them, and in doing so, writing those events into the permanent history of the cosmos. However, this consciousness-centric view is highly controversial and faces a formidable challenge from a more mainstream framework within physics, decoherence theory. Decoherence explains the transition from quantum to classical without invoking any mysterious role for consciousness. It argues that measurement isn't a special physical process, but an inevitable consequence of interaction. A quantum system, like an atom, is never truly isolated. It is constantly bombarded by and interacting with its environment, air molecules, photons, background radiation. These countless tiny interactions effectively measure the system, causing it to lose its quantum coherence extremely rapidly. The information about the system's state isn't destroyed. It is rapidly copied and disseminated into the environment in a way that makes the original superposition inaccessible for all practical purposes. The world appears classical not because a mind is looking, but because the universe is perpetually and uncontrollably looking at itself. From the decoherence perspective, a conscious observer is simply a very complex macroscopic system that has itself undergone extensive decoherence. When a scientist reads a measurement device, they are not causing a collapse. They are just one more link in a long chain of entanglements that began with the quantum system and its immediate environment. The cosmic memory is being written by every interaction, conscious or not. A tree falling in a forest with no one around absolutely makes a sound because the air molecules and the ground act as the recording medium, faithfully encoding the information of the event through their interactions long before any human ear could hear it. This philosophical divide forces us to confront the deepest questions about our place in the universe. Are we, as conscious beings, fundamental actors without whom the cosmic story cannot be written? Or are we merely sophisticated readers, latecomers to a universe that has been diligently keeping its own records through physical processes since the beginning of time? The answer may determine whether cosmic memory is a shared, objective archive waiting to be discovered, or a profoundly personal creation brought into being by the very act of our looking. However, this incredible capacity for memory across the cosmos comes with a profound and sobering caveat, governed by the most relentless law in all of physics, the second law of thermodynamics. This law, which states that the total entropy or disorder of an isolated system can never decrease over time, isn't just a rule about messy rooms. It's the very engine of the arrow of time and the ultimate arbiter of what can be remembered and for how long. While the universe seems wired to preserve information, the process of retrieving that information, of actually reading the cosmic ledger, is a constant battle against this rising tide of entropy. Every act of remembrance, whether in our brains or in a particle detector, requires work, and that work always comes at a cost, adding a little more disorder to the universe in the process. This intimate link between information and thermodynamics was crystallized by the physicist Rolf Landauer in the 1960s. He proposed a stunningly simple yet profound principle: that erasing information is a fundamentally physical process that must dissipate energy as heat. Think about a single bit of computer memory. To reset that bit to a zero, regardless of what it was before, you have to irreversibly lose the information it once held. Landauer proved that this act of erasure isn't free. It requires a minimum amount of energy to be expended, and that energy is converted into heat, increasing the entropy of the surrounding environment. This means that forgetting isn't just an abstract concept, it's a thermodynamic event. Conversely, to store information, you have to create a low-entropy, highly ordered state, which also requires energy. So the universe's memory system is constantly fighting an uphill battle, expending energy to create local islands of order where information can be written, while the vast ocean of the cosmos trends inexorably toward a featureless equilibrium. To understand the fragility this imposes, imagine trying to listen to an old, magnetic tape recording of a priceless historical speech. As the tape ages, the magnetic particles holding the information slowly become misaligned due to thermal agitation and environmental factors. The recording degrades, hiss and static random noise begin to overwhelm the original signal. You can still play the tape, but retrieving the clear, original information becomes harder and harder. Eventually, the signal is lost entirely in the noise. This is a perfect analogy for the cosmic struggle with entropy. The universe has written the data of its history into gravitational waves, quantum foam, and magnetic fossils, but as entropy increases, the noise of random particle motion and thermal energy makes it increasingly difficult to distinguish that precious signal. The information might still be there in principle, as mandated by quantum mechanics, but it becomes so scrambled and diluted that it is effectively lost, just like a message whispered into a hurricane. This brings us to the most ultimate and somber cosmic eventualities, the heat death of the universe. In this far, far future scenario, trillions upon trillions of years from now, the acceleration driven by dark energy will have pushed all galaxies beyond our observable horizon. The last stars will have long since burned out, and even the supermassive black holes will have evaporated away via Hawking radiation. The universe will approach a state of maximum entropy, a lukewarm, incredibly dilute sea of particles and radiation where the temperature is uniform everywhere. In this state, no energy gradients exist. There are no hot spots or cold spots, no work can be done, and no processes can occur. It is the end of time in any meaningful sense. In this final equilibrium, the cosmic memory still exists, encoded in the microscopic configuration of all those particles, but with no energy available to power a computer, a brain, or any kind of observer, there is no way to retrieve that information. The universe's entire history, from the brilliant flash of the Big Bang to the silent fade of the last star, becomes a closed book with no one left to read it. The ledger is permanent but utterly inaccessible, a monument to itself in an empty museum. This is the delicate balance of cosmic memory, eternally preserved in theory, but increasingly fragile and hidden in practice, a testament written in fading ink on the pages of time. While we've explored messages carried by light, gravity, and quantum connections, some of the universe's most direct and visceral dispatches arrive not as waves or ripples, but as solid matter itself, screaming across the cosmos at nearly the speed of light. These are cosmic rays, not rays at all, but atomic nuclei, mostly protons, that have been accelerated to energies so immense they defy belief. They are the universe's high-speed couriers, and they carry within them an encoded story of the most violent and powerful engines in existence. When one of these particles slams into Earth's atmosphere, it creates a spectacular secondary shower of particles, a cosmic fireworks display that is the only way we can detect these messengers from the depths of space. Each one is a piece of shrapnel from a celestial catastrophe, a physical sample of an event that happened light years away, and by catching them, we are collecting evidence from the scene of the crime. To understand the sheer power these particles carry, consider the famous "Oh my God" particle, detected back in 1991 by the Fly's Eye Observatory in Utah. This was not your average cosmic ray. It was a single subatomic particle, most likely a proton, but it was traveling with so much kinetic energy that it was moving at 99.9999999999995% of the speed of light. To put that incomprehensible number into perspective, this single tiny particle had the kinetic energy of a well-thrown baseball, all compressed into a space 1,000,000,000,000 times smaller. It was moving so fast that, due to the effects of special relativity from its own perspective, it could have crossed the entire observable universe in a matter of days. The existence of such a particle is a monumental puzzle. What natural particle accelerator in the universe could possibly be powerful enough to give a proton such a staggering kick? Our best theories for acceleration, involving shock waves from supernova or the intense magnetic fields around active black holes, strain to explain such extreme energies. This one particle is a message that challenges our very understanding of physics, a cosmic memory that tells us we are still missing a fundamental piece of the puzzle. To catch these elusive and rare high-energy messengers, we have built some of the most ambitious and vast experiments on Earth. The Pierre Auger Observatory in Argentina is a premier example, an array of detectors sprawled across an area of 3,000 square kilometers, a footprint nearly the size of Rhode Island. It doesn't try to catch the primary cosmic ray itself, which is too rare to hit a small detector. Instead, it watches for the extensive air shower it creates. When an ultra-high-energy cosmic ray collides with a molecule in the upper atmosphere, it triggers a cascade of billions of secondary particles that rain down over an area of many square kilometers. The Auger Observatory uses 1,600 water tank detectors spaced across the plains to sense the particles that reach the ground, while a set of fluorescence telescopes watches the night sky to capture the faint ultraviolet light emitted by the shower as it develops. By combining these two techniques, scientists can perform a remarkable feat of cosmic reconstruction. They can calculate the original particle's energy, its direction of travel, and even make an educated guess about its mass, allowing them to trace its path back across the interstellar void to its probable source. The metaphor for this is powerfully simple. It is like finding a message in a bottle washed up on a shore. The vast, empty ocean between galaxies is the sea. The cosmic ray is the bottle thrown into the water by a violent event on some distant shore, a supernova explosion, a merging black hole, or a hyperactive galactic nucleus. The message inside the bottle is the information encoded in the particle's energy, its type, and its direction of travel. Our detectors on Earth are the shoreline where these bottles occasionally wash up. By carefully studying the bottle, its seal, its paper, its handwriting, and by noting the direction from which the currents brought it, we can make inferences about where it came from and what happened there. We may not know the exact beach it launched from, but we can identify the general region of the ocean, and we can read the story of the storm that cast it adrift. In this way, each high-energy cosmic ray is a tangible piece of a distant event, a physical memory delivered directly to our doorstep. This method has already borne incredible fruit. Data from the Auger Observatory and other facilities have provided strong statistical evidence that the very highest energy cosmic rays are not coming from random points in the sky. They appear to be correlated with extragalactic sources, particularly with nearby active galaxies whose colossal black holes are devouring matter and blasting out unimaginable amounts of energy. These particles are the byproduct of that frenzy, the exhaust fumes from the universe's most powerful engines. By mapping their arrival directions, we are slowly sketching a map of the most violent neighborhoods in our local cosmic volume, building a picture of where the universe's most energetic particle accelerators are located. This transforms cosmic rays from mere curiosities into essential tools for astrophysics. providing a unique window into processes that are often hidden from traditional telescopes by cosmic dust or because they don't produce much visible light. They are the hard evidence, the smoking gun, proving that the universe's most dramatic events don't just send out energy, they literally fire bullets of matter across the cosmos, each one a permanent, indestructible record of the incredible forces that created it. Yet to truly grasp the universe's ultimate memory system, we must venture to the very edge of our understanding, to a realm where the familiar rules of reality break down completely. This is the frontier of quantum gravity, the long-sought theory that aims to unite Einstein's majestic picture of curved spacetime with the bizarre, probabilistic world of quantum mechanics. It is here, at this profound intersection, that we might finally discover the most fundamental medium of all for cosmic memory, the very fabric of spacetime itself, woven from unimaginably tiny threads at the Planck scale. The quest to understand this isn't just academic. It's a search for the universe's original and most permanent hard drive, operating at sizes a billionth of a billionth of a billionth of a meter. The central problem that quantum gravity must solve is a clash of titans. General relativity describes spacetime as a smooth, continuous, and dynamic stage that curves and warps in response to matter and energy. Quantum mechanics, on the other hand, tells us that everything else, matter, light, forces, is granular, made of discrete, quantized packets of energy. So why should spacetime itself be any different? The concept of the Planck length, a distance of about 10 to the negative 35 meters, provides a powerful hint. This isn't just another small number. It's the scale at which the quantum fluctuations of spacetime itself are predicted to become so violent that the very notions of here and there cease to have any meaning. It is the natural limit of resolution for reality, suggesting that if we could peer down to this level, the smooth stage of spacetime would dissolve into a seething, chaotic foam. Many physicists believe that at this scale, spacetime is not continuous but is instead composed of fundamental, discrete units, the universe's most basic pixels. This idea of a pixelated reality is at the heart of several competing approaches to quantum gravity. String theory, for instance, proposes that the fundamental entities are not point-like particles but incredibly tiny, vibrating loops of energy. The different vibrations of these strings give rise to all the different particles and forces we see. But crucially, the theory requires extra spatial dimensions, curled up at the Planck scale, and the geometry of these dimensions dictates the laws of physics in our observable universe. In this view, the memory of how those dimensions are compactified is permanently encoded into the structure of everything, a fundamental data set that defines reality from the bottom up. A different yet equally compelling approach is loop quantum gravity. This framework suggests that space itself is not a background arena, but is woven from a network of intersecting loops, forming a fabric of finite, quantized grains. Think of it as a cosmic chainmail vest, where each interlocking link represents a tiny, indivisible unit of space. The entire geometry of the universe, its volume, its shape, emerges from the connections between these loops and the quantum numbers associated with them. In this spin network, as it's called, information isn't stored in space, it is space. The history of the cosmos would be written in the evolving connections of this network, a dynamic tapestry where every event adds a new knot or changes a connection, forever altering the fundamental structure of reality at the smallest possible scale. A third fascinating proposal is causal set theory. This approach posits that the fundamental building blocks of spacetime are discrete events, and the only thing that matters is the causal relationship between them, which event can influence which other event. The smooth, four-dimensional spacetime of our experience emerges as a coarse-grained approximation of this underlying network of cause and effect. In this view, the universe's memory is its own causal history. The entire timeline of events, from the Big Bang to the present, is fundamentally a vast, ordered set of points, and the information about the cosmos is stored in the intricate web of connections that define what led to what. It is a universe built not on space, but on pure relationship and history. To visualize how these discrete units could store information, consider a breathtakingly high-resolution digital photograph on your screen. From a normal viewing distance, the image appears smooth and continuous, with flowing gradients of color and light. But if you zoom in far enough, you see that this illusion is created by a finite number of individual pixels, each one a single, solid color. The complete image is nothing more than the specific arrangement and color values of every one of those pixels. Now, imagine the universe is that image. The stars, galaxies, and people are the large-scale, smooth-looking features, but the underlying reality is a vast array of Planck-scale pixels. A theory of quantum gravity would be the code that tells us how to translate the information stored in each pixel, perhaps its spin, its volume, or its connection to neighbors, into the laws of physics and the content of the cosmos we observe. A gravitational wave passing through would be a specific pattern of changes rippling through this pixelated grid. The mass of a planet would be information encoded in the density and arrangement of these fundamental units of space. This means that every event that has ever occurred, from the formation of a black hole to the firing of a neuron in your brain, has left its mark not just on the surface of space-time, but in its very weave. The universe remembers by literally restructuring itself at the most fundamental level. The past is not a ghostly abstract concept. It is physically etched into the geometry of the quantum gravitational field. Unlocking this code, learning to read the memory stored in these Planck-scale pixels, represents the next great revolution in physics. It would grant us the ultimate cosmic perspective, allowing us to see not just what the universe is doing, but how it is built, revealing that every moment of its history is forever frozen in the exquisite, granular structure of spacetime itself. But even as we map the visible universe and its known forces, there are unexplained currents moving on the largest scales imaginable, mysterious flows that hint our cosmic neighborhood might be shaped by realms we cannot see. One of the most profound and controversial of these mysteries is a phenomenon known as dark flow. Imagine you're floating in the middle of a vast, seemingly endless ocean. The water around you is calm, and you assume you're adrift in a featureless sea. But then you notice something strange. All the debris, leaves, pieces of wood, even other boats, are all drifting slowly but unmistakably in one specific direction, pulled by a deep, unseen current. This is the essence of dark flow. It's the observation that entire galaxy clusters, thousands of them, appear to be moving in a coordinated, bulk motion toward a specific point on the edge of the observable universe, as if they are all being tugged by something immense lying far beyond our horizon. This isn't a small, local motion. We're talking about clusters of galaxies, each containing hundreds or thousands of galaxies, all moving at velocities of over 600 miles per second in the same general direction. This motion is separate from the overall expansion of the universe described by Hubble's law. It's an additional, peculiar velocity that seems to affect matter on a scale of billions of light years. The force required to create such a coherent motion on such an unimaginably vast scale would have to be almost incomprehensibly powerful, far exceeding the gravitational pull of any known supercluster or cosmic structure within our view. This is what makes dark flow so tantalizing and so unsettling. It suggests an influence whose source lies outside the volume of space we can possibly observe. So what could possibly be exerting this gravitational pull from beyond the edge of everything we know? The most mind-bending possibility is that this flow is a gravitational memory, an imprint from the epoch before cosmic inflation. Our observable universe is just a tiny bubble, a region that was inflated from a microscopic patch of the primordial cosmos. But what if that initial patch was not perfectly isolated? What if it was near something else, another region of space-time, another universe entirely in a vast multiverse? The gravitational pull from that other, unseen universe, from beyond our inflationary bubble, could have been locked in during the initial moments of expansion, creating a persistent tug that has been pulling on our entire observable cosmos for 13.8 billion years. In this scenario, dark flow is the universe remembering its birth environment, a fossilized gravitational vector pointing toward a neighboring reality we can never directly visit. The primary tool for detecting this subtle motion is once again the cosmic microwave background. Scientists use it as a fixed reference frame, the ultimate backdrop against which all other motions can be measured. The technique involves studying the CMB's temperature in the direction of these moving clusters. As a cluster moves toward us, the photons of the CMB that pass through it undergo a subtle energy shift due to the kinetic Sunyaev-Zeldovich effect. By meticulously measuring this tiny distortion for thousands of clusters, astronomers can triangulate their peculiar velocities and see if they exhibit a preferred direction. The teams that have reported evidence for dark flow, like those working with data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, have found that this flow seems to be coherent across staggering distances, aligning with a specific patch of sky between the constellations of Centaurus and Vela. However, this is where the mystery deepens into intense scientific debate. The statistical significance of the dark flow signal is hotly contested. Other analyzers of the same data have argued that the detected motion could be the result of systematic errors, instrumental noise, or the incomplete masking of foreground emissions from our own galaxy. The controversy is a perfect example of science at the frontier, where researchers are pushing instruments to their absolute limits to detect signals that are barely distinguishable from the background hum of the cosmos. The quest to confirm or refute dark flow is ongoing, driving the need for more precise future CMB experiments that can measure these minute effects with even greater accuracy. Beyond dark flow, other large-scale anomalies add to the intrigue. The CMB itself has a curious hemispheric asymmetry. One half of the sky has slightly larger temperature fluctuations than the other. There's also the mysterious cold spot, an unusually large and cold region in the CMB that some have speculated could be the imprint of a collision with another universe during inflation. While each of these anomalies could have more conventional explanations, together they paint a picture of a cosmos that might not be as uniform and isotropic as we once believed. They are like faint cracks in the facade of reality, hints that our standard model of cosmology, while incredibly successful, might be incomplete. The metaphor of the ocean current is powerfully apt here. We are like sailors who have only recently begun to chart our immediate waters. The coordinated drift of galaxy clusters is our first hint of a vast, distant storm system over the horizon, its presence revealed only by the relentless pull it exerts on everything in our sea. These large-scale flows are not random noise, they are potential carriers of information, cosmic telegrams from realms beyond our light cone. They remind us with breathtaking force that the universe's memory is not necessarily confined to the volume we can see. The complete history of existence may be written in a library whose full shelves extend into a darkness we are only just beginning to sense, and every strange, unexplained motion is a clue waiting to be read. But what if the universe's grandest memory systems are not just echoed in the vastness of space, but are mirrored within the most intricate structures of life itself? This brings us to a breathtakingly beautiful and interdisciplinary connection, the profound parallels between the ways biological systems store information and the cosmic processes that govern the entire universe. It's a concept that suggests the same fundamental principles of memory and information might be operating from the scale of our own neurons all the way out to the large-scale structure of the cosmos, hinting at a deep, underlying unity in how reality organizes and preserves its story. Let's start with the most fundamental biological memory system of all, DNA. This magnificent molecule is quite literally a chemical instruction manual, a double helix that uses a 4-letter alphabet of nucleotides to encode the entire blueprint for building and operating a living organism. It is a robust, durable storage medium, capable of preserving information across generations, from the first single-celled organisms billions of years ago to the incredible diversity of life we see today. Now compare this to the cosmic microwave background radiation. The CMB is the universe's own genetic code. Its tiny temperature fluctuations are like nucleotides, a simple binary of slightly hotter and slightly colder patches. This pattern isn't random noise. It is a detailed blueprint that encoded the entire future, large-scale structure of the universe, where galaxies would form, where vast voids would exist. In both cases, a relatively simple code, written at a foundational moment, unfolds into an astonishingly complex and diverse reality over immense spans of time. The universe, in a very real sense, has its own DNA, and we can read it in the ancient light that fills the sky. The parallels become even more striking when we examine the architecture of information networks. Inside our own brains, memory is not stored in one single location like a file on a hard drive. It is distributed across a vast, interconnected network of neurons. Each memory is a specific pattern of synaptic connections and strengths, a unique pathway of firing neurons that lights up when we recall a face, a place, or a feeling. This neural network is a web of relationships, and its power comes from its interconnectedness. Now, look up at the cosmic web revealed by our most powerful telescopes. This is the large-scale structure of the universe, a sprawling network of galaxies strung along filaments of dark matter, with immense, empty voids between them. The resemblance is uncanny. Both systems are complex networks where the nodes, neurons in the brain, galaxies in the cosmos, are less important than the connections between them. In both cases, the structure itself, the pattern of connections, is the information. The cosmic web is the universe's brain, and the galaxies are its neurons, firing not with electricity but with the light of billions of stars. This leads to a fascinating and controversial theory that directly connects biological memory to cosmic memory, panspermia. This is the idea that the basic ingredients for life, or even life itself in a dormant state, could be distributed throughout space, hitchhiking on comets, asteroids, or interstellar dust. If this theory holds, then every living organism on Earth might carry within it a physical memory of a cosmic journey. Your very DNA could contain molecular remnants that originated around a distant star in a solar system that no longer exists. The building blocks of life, amino acids and nucleobases, have already been found in meteorites and in the clouds of gas between stars. This suggests that life on Earth may not have started from absolute scratch. It might have been seeded with a starter kit from elsewhere in the galaxy. In this view, biology becomes a vessel for cosmic memory, a living library preserving chemical information about its interstellar ancestry. A bacterium frozen in a comet's ice is a time capsule, and a spore drifting between stars is a message in a bottle, carrying the potential for life and the memory of its origin across the light years. We can push this analogy even further with the powerful metaphor of a seed. An acorn is a perfect, compact package. It doesn't contain a miniature oak tree, but it does contain the entire informational blueprint, the DNA, needed to grow one, given the right conditions of soil, water, and sunlight. It is a biological memory of its parent tree, a promise of a future forest. Now, imagine a prebiotic molecule, a complex organic compound floating in the protoplanetary disk of a young star. This molecule is a cosmic seed, under the right conditions, on a suitable planet with liquid water and a stable environment. This chemical seed could trigger the process of abiogenesis, the emergence of life. It carries within its structure a kind of chemical memory, a set of instructions for complexity waiting to be unlocked. This creates a beautiful continuum, from the cosmic seed of a complex molecule to the biological seed of a plant, to the informational seed of the CMB's fluctuations. At every scale, reality seems to operate on a principle of encoding potential into a compact form, which then unfolds into the magnificent complexity we observe. This interdisciplinary angle does more than just provide relatable comparisons. It enriches our entire narrative of cosmic memory. It suggests that the drive to record, to preserve, and to transmit information might be a universal principle, manifesting in the gravitational dynamics of galaxies, the quantum vibrations of space-time, and the biochemical processes of life. We are not separate from the cosmos that we study. We are a part of its memory system. Our own consciousness, our ability to observe the universe and wonder about its origins, might be the universe's way of becoming aware of itself, of reading its own story. The memories are not just out there in the void. They are literally written into us, in our genes and in our minds, connecting the most intimate aspects of our being to the grandest scales of existence in one continuous, breathtaking thread of information. To grasp how the cosmos could safeguard its memories against the relentless pull of chaos and decay, we must journey into the most abstract and mathematically beautiful realm of physics, quantum information theory. This isn't just about how we might build better computers. It's about providing a fundamental language to describe how the universe itself might process and preserve data across cosmic scales and deep time. At its heart are the qubits, the fundamental units of quantum information. Unlike a classical computer bit, which can only be a 1 or a 0, a qubit can exist in a superposition of both states simultaneously, a delicate and powerful condition that forms the basis of quantum computing's potential. But this superposition is incredibly fragile, vulnerable to any interaction with its environment, a process called decoherence that swiftly destroys the quantum magic, collapsing the possibilities into a single, classical reality. For the universe to maintain a long-term memory of quantum events, it would need a way to protect this information, to shield it from the erasing effects of decoherence. This is where the concept of quantum error correction enters the cosmic story, offering a potential mechanism for near-perfect preservation. The core idea of quantum error correction is as ingenious as it is counterintuitive. You cannot simply copy a qubit to back it up, as the quantum no-cloning theorem forbids it. Instead, you must spread the information of one logical qubit across a highly entangled network of many physical qubits. Think of it like protecting a precious, fragile vase by shattering it into pieces, encrypting the instructions for its reassembly, and then distributing those fragments among a trusted group of friends. If one friend loses their piece, or if it gets damaged, you can still recover the complete vase because the information for its reconstruction is holographically stored across the entire group, not in any single fragment. A quantum error correcting code does precisely this. It encodes the information so that the most likely types of errors, a flip or a phase shift in one of the physical qubits, become detectable and correctable without you ever having to directly measure and collapse the fragile logical qubit itself. The true information is not in the individual components, it is in the correlations between them. This theoretical framework provides a stunningly elegant potential solution to the black hole information paradox that has troubled physicists for decades. The work of theorists like Patrick Hayden and others suggests that the event horizon of a black hole might not be a destructive boundary but the ultimate quantum error correcting system. When matter and information fall into a black hole, they don't vanish into the singularity never to be seen again. Instead, the information becomes wildly scrambled and encoded across the entire surface area of the event horizon, a process known as quantum scrambling. From the outside, this information is not lost. It is merely transformed into an excruciatingly complex form, much like a document put through a cryptographic cipher. Hayden's research, particularly with colleagues on the concept of black hole mirrors, explores how this scrambled information might be recovered from the Hawking radiation that the black hole slowly emits. It would be like reconstituting that shattered vase from the smoke and heat rising from a fire, a seemingly impossible task that quantum mechanics might actually allow. The black hole, in this view, is not a cosmic shredder but a sophisticated quantum computer, performing the most extreme data storage and retrieval operation imaginable. A powerful analogy to understand this cosmic redundancy is a modern computer's RAID array. In a RAID system, data is not stored on a single hard drive where a failure would mean total loss. Instead, the data is striped and mirrored across multiple drives. If one drive fails, the system can use the parity information stored on the others to rebuild the lost data seamlessly, without the user ever noticing an interruption. The universe might be operating on a similar principle, but at a fundamental level, the information that defines a particle or an event isn't stored in one place. It is distributed, perhaps holographically, across a wider region of spacetime, protected by the inherent redundancy of quantum entanglement. The vacuum of space itself, with its seething quantum foam, might be threaded with these error-correcting codes, ensuring that information about the past is never truly erased, only ever more deeply integrated into the cosmic network. This transforms our view of empty space from a simple void into a dynamic, error-resilient storage medium. This technical perspective reveals a universe of astonishing sophistication, where the preservation of memory isn't a happy accident but a fundamental consequence of the laws of physics. The same principles that might one day protect the fragile calculations of a quantum computer could be the very mechanisms that have allowed the cosmos to remember its own history for billions of years. It suggests that information is the most durable currency in the universe, and the laws of physics are its ultimate guardians, employing every trick of quantum entanglement and non-locality to ensure that not a single bit is ever truly lost, only waiting to be decoded by a mind capable of understanding the cipher. But if the grand architecture of galaxies and the strange logic of quantum error correction form one layer of the cosmic memory, there exists an even more fundamental and ubiquitous substrate, one that is present in every cubic centimeter of what we call empty space. This brings us to the quantum vacuum, a seething ocean of pure potential that is anything but empty. We often think of a perfect vacuum as a void, a complete nothingness. But quantum physics paints a radically different picture. What we perceive as empty space is in fact a dynamic medium teeming with so-called zero-point energy. This is the lowest possible energy that a quantum mechanical system may have, and it is anything but zero. Thanks to the Heisenberg uncertainty principle, which forbids any particle from ever being completely at rest. The vacuum is alive with fleeting fluctuations. Pairs of virtual particles, a particle and its antiparticle, constantly blink into and out of existence, borrowing energy from the vacuum for an unimaginably short time before annihilating each other and paying the debt back. This isn't just theoretical. We can observe the effects of this frenzy, and it suggests that the vacuum itself might be the universe's most fundamental and widespread memory device. The question then becomes, how could this chaotic, temporary process possibly store lasting information? The key lies not in the individual particles, which are here and gone in a flash, but in the overall state and structure of the vacuum itself. The rate and nature of these fluctuations are not random. They are dictated by the boundary conditions and the energy density of the space they occupy. A region of empty space far between galaxies has one fluctuation profile, but the vacuum near a massive star, or more intriguingly, squeezed between two closely placed metal plates, has a completely different one. This is the famous Casimir effect, a stunning experimental validation of zero-point energy. When two conductive plates are brought extremely close together in a vacuum, they actually experience a slight but measurable force pushing them together. This happens because the plates restrict the kinds of quantum fluctuations that can occur in the space between them. Only those virtual particles whose wavelengths fit perfectly between the plates can pop into existence there, while outside the plates all wavelengths are possible. This creates a pressure differential, with more virtual particles pushing on the outside of the plates than on the inside, forcing them together. The vacuum between the plates remembers the presence of the boundaries, and that memory manifests as a physical force. This leads to a profound possibility. Every massive object that has ever existed in the universe, every star, every planet, every human being has a gravitational field. That gravitational field subtly warps the space around it, altering the energy density of the vacuum in its vicinity. This, in turn, changes the statistical dance of virtual particles in that region of space. That alteration is a permanent, if infinitesimally small, change in the vacuum state. Long after the object is gone, the vacuum in that region might retain a faint statistical echo, a persistent correlation that remembers the geometry and energy that once shaped it. It's as if the vacuum has a kind of quantum elasticity. You can stretch and bend it, and even after the force is removed, it retains a memory of the deformation in the pattern of its fluctuations. A powerful way to conceptualize this is to think of the quantum vacuum as a perfectly calm sea on a windless day. From a distance, the surface appears flat and featureless, a blank slate. But beneath the surface, powerful currents and eddies flow, created by winds that blew days or even weeks ago. These underwater currents are the vacuum fluctuations, and they remember the patterns of the past weather. A skilled oceanographer could, by measuring these subtle flows, reconstruct the history of storms that had long since passed. In the same way, a hypothetical physicist with sufficiently sensitive instruments might, by probing the detailed statistics of the quantum vacuum in a region of space, detect the faint residual signature of a massive object that had once occupied that space, or a powerful energy event that had temporarily warped it. The vacuum would hold that memory latently, not as a recorded image, but as a persistent statistical preference in its ceaseless quantum dance. This transforms our view of the cosmos yet again. It suggests that the universe's memory is not just stored in light, or in gravity, or in matter, but in the very fabric of space itself. The vacuum is not a passive stage, it is an active participant, a medium that is continuously written upon by every event and every object, and which retains those impressions in the most subtle and fundamental way imaginable. It is the ultimate ledger, present everywhere at once, recording the history of reality not in bold strokes, but in the whisper-quiet statistics of an eternal quantum storm. But as we marvel at the universe's apparent drive to remember, we must also confront a powerful, opposing cosmic principle, one that suggests some information might be placed permanently off-limits, sealed away behind the ultimate privacy barrier. This brings us to the profound and still unproven cosmic censorship hypothesis, a bold conjecture put forward by the legendary physicist Roger Penrose. At its heart, this idea is a rule about cosmic decorum, a proposal that the universe possesses a fundamental modesty, preventing its most terrifying and lawless regions from ever being exposed to public view. These regions are singularities, points of infinite density where the known laws of physics completely break down, and concepts of space, time, and causality cease to have any meaning. The cosmic censorship hypothesis asserts that nature abhors a naked singularity. It proposes that every singularity must be decently clothed, forever hidden from the outside universe by a protective veil known as an event horizon. To understand why this is so crucial, consider the chaotic nightmare a naked singularity would represent. Inside the event horizon of a black hole, the singularity is contained. Its unpredictable, physics-shattering nature is quarantined, unable to affect the orderly universe outside. But a naked singularity, one without an event horizon, would be a tear in the very fabric of causality. It could spit out information and influence at random, with no regard for the laws of cause and effect. An observer could watch as a spaceship approaches the singularity and is utterly destroyed, its information scrambled into pure randomness. But then, a moment later, the singularity might spontaneously reassemble the spaceship and its crew from nothingness and spit it back out. The predictable, classical universe we rely on would be impossible. Physics could offer no forecasts, and the very concept of a stable, objective reality would dissolve into chaos. The cosmic censorship hypothesis is essentially a statement that the universe values order and predictability above all else, and it enforces this by placing its most dangerous elements under permanent house arrest. This act of cosmic quarantine has a direct and profound implication for information preservation. An event horizon doesn't just hide a singularity, it regulates the flow of information. It acts as a one-way membrane, allowing information to fall in but preventing any internal information from escaping. In this way, it protects the external universe from the unpredictable information loss and gain that would emanate from a naked singularity. The horizon doesn't destroy information. It simply places it in a vault from which it cannot causally influence the outside world. This creates a stable boundary between the knowable and the unknowable, ensuring that the universe's memory, the reliable chain of cause and effect that we can observe and record, remains coherent and consistent. The event horizon is the universe's ultimate archivist, deciding which information remains accessible to the cosmic ledger and which is filed away in a section marked forever closed. Roger Penrose's contributions to this narrative extend far beyond censorship into an even more spectacular vision of cosmic memory. His theory of conformal cyclic cosmology is one of the most audacious ideas in all of modern physics. It proposes that our universe is not the first and only one, but merely one eon in an endless cycle. In this model, the distant heat-death fate of our universe, a vast, empty, cold expanse of diluted particles and low-energy photons, becomes mathematically indistinguishable from the high-energy, ultra-dense initial state of a new Big Bang. Penrose suggests that at this point of transition, a conformal rescaling of spacetime could connect the infinite future of one eon to the explosive beginning of the next. But what happens to information? Penrose speculates that gravitational information, in the form of the universe's conformal geometry, might somehow be transferred across this boundary. It's a concept that redefines permanence, suggesting that the memory of one universe could subtly imprint itself upon the next, like a faint watermark on the first page of a new volume in an infinite series. A powerful analogy for this cosmic regulation is to think of an event horizon as the ultimate quarantine zone for dangerous information. Imagine a highly contagious and reality-warping virus is discovered, a pathogen that doesn't affect biology, but instead scrambles the very laws of logic and physics. The only safe way to handle it is to immediately seal it inside a perfect, impenetrable biocontainment facility. Nothing inside can get out, and its chaotic influence is utterly contained. The scientists outside can study the facility's boundary, they can know something is inside, and they can even send probes in, but the chaos within cannot leak out to infect the sane, orderly world. The event horizon serves this exact purpose for the singularity. It is the universe's own maximum security containment unit, ensuring that the unpredictable, lawless information of the singularity cannot leak out and corrupt the causal structure of the cosmos we inhabit. This highlights a breathtaking duality in how cosmic structures manage information flow. On one hand, we have mechanisms like quantum entanglement and the holographic principle that seem designed to proliferate and preserve information, to make it widely available and redundant. On the other hand, we have event horizons and cosmic censorship, which seem designed to hide and restrict information, to create permanent and absolute boundaries to knowledge. This isn't a contradiction, it's a sophisticated system of information governance. The universe appears to have both a prolific publishing arm, constantly broadcasting data via light and gravity, and a strict classification system that redacts anything that could threaten the overall stability of reality. It suggests that cosmic memory isn't about recording everything without judgment, but about curating a stable, consistent, and knowable history, even if that means permanently sealing away the chapters that are too dangerous to read. But what if the ultimate fate of cosmic memory isn't a slow fade into darkness, but a dramatic, cyclical rebirth? This brings us to one of the most captivating alternatives to the standard Big Bang narrative, the ekpyrotic universe model, and its broader class of cyclic cosmologies. These theories propose a breathtaking vision of existence without a true beginning or end, where the cosmos undergoes endless cycles of contraction, collision, and renewal. In this grand, rhythmic dance, the universe might not be a single, linear story but an infinite-volume epic, with each chapter ending in a fiery convergence that seeds the next. The question of memory becomes even more profound here. Could information not only survive within a cycle but actually be transferred from one cosmic epoch to the next, creating a chain of remembrance spanning eternity? The ekpyrotic model, whose name is derived from the Greek word for conflagration or fire, was developed by physicists Paul Steinhardt and Neil Turok. It envisions our four-dimensional universe as a three-dimensional membrane, or brain, floating within a higher dimensional space. Nearby, there exists another parallel brain, a hidden world separated from us by an extra-spatial dimension. In this model, the Big Bang was not a singularity emerging from nothing, but a spectacular event triggered when these two brains, moving through the higher dimensional bulk, collided with each other. The immense energy of this collision flooded our brain, creating all the matter and radiation we see today, and igniting the expansion we are still experiencing. But this is not a one-time event. The model proposes that the brains are attracted to one another, destined to pull apart and then come crashing together again and again in a never-ending cycle. This cyclical nature is the key to its potential as a memory-preserving mechanism. After the collision, the brains bounce apart, and our universe enters its expansion phase, much like the one we observe today. Eventually, dark energy's influence wanes, and the gravitational attraction between the brains pulls them back together. The universe contracts, heading toward the next collision, which becomes the next Big Bang. Crucially, Steinhardt and Turok's work shows that these cycles can be structured to avoid a true singularity, a point of infinite density where all laws of physics break down and information is thought to be lost. Instead of a catastrophic crunch, the collision is a smooth, calculable event governed by string theory. Because there is no singularity to act as an information shredder, the door is left open for data from the previous cycle to, in some form, make it through the transition. So how might information actually survive the fire? The brains themselves are the likely carriers. Think of a brain not as an inert sheet, but as a dynamic entity with its own structure and vibrational modes. The specific way a brain vibrates, its topology, and the fields that live on it could all encode information. As the brains collide and bounce apart, these properties might not be completely erased. Certain universal constants, the fundamental parameters of physics, or even the large-scale geometrical imprint of the previous cycle, could be inherited by the new one. It's not that every star and planet would be reborn exactly as it was. That specific information is almost certainly scrambled by the immense energy of the collision. But the potential for complexity, the underlying rules of the game, could be preserved. The new cycle would begin not with a random set of laws, but with a legacy, a cosmic genetic code passed down from its parent universe. A powerful metaphor for this is the mythical phoenix. The bird is consumed by flames in a spectacular display, and from its ashes it is reborn, rising again with its essence and identity intact. In the cyclic universe model, the fiery collision of the brains is the conflagration. The entire cosmic structure, galaxies, stars, planets, is reduced to a primordial state of energy. But the ashes, in this case, are the brains themselves and the fundamental information etched into their fabric. The new universe that expands from the collision is the phoenix, reborn with the same physical laws and perhaps even a faint, statistical echo of its previous form, ready to build a new world from the old blueprint. The memory is not of specific events, but of potentiality itself. This offers a radically different and deeply poetic narrative for the persistence of cosmic memory. Instead of a single, finite universe fighting a losing battle against entropy, we have an eternal, cyclical cosmos where information is periodically refreshed and renewed. The ledger is not closed at heat death. It is wiped clean for a new entry, but the cover and the binding, the fundamental laws encoded on the brains remain the same. It transforms the cosmos from a one-off performance into an endless symphony, with each movement beginning from the resonant memory of the last. While we stand on the shoulders of giants, peering into the past with today's incredible tools, the future of cosmic archaeology promises to revolutionize our understanding in ways we can only begin to imagine. We are on the cusp of a new era, not just of bigger telescopes, but of entirely new ways of sensing the universe, technologies that will allow us to read the faintest whispers of history written into the fabric of reality itself. This isn't merely about improving our vision. It's about developing entirely new senses to perceive the cosmos. Think of our current situation as trying to understand the entire plot of a complex, epic novel by only reading every 10th page. The next generation of instruments will give us every single word, and perhaps even the hidden meanings between the lines. One of the most anticipated ventures is the Laser Interferometer Space Antenna, or LISA. This is not just an upgrade to ground-based observatories like LIGO. It is a fundamentally different kind of instrument. Imagine constructing a gravitational wave telescope so vast that its 3 spacecraft form a perfect equilateral triangle, with each side 2.5 million kilometers long, orbiting the Sun behind Earth. This colossal scale will allow LISA to detect gravitational waves at frequencies far lower than any ground-based detector can perceive. It will tune into a whole new channel of cosmic history, listening for the slow, stately mergers of supermassive black holes at the hearts of galaxies, events that shape the entire evolution of the cosmic web. It might even hear the faint, primordial hum from the instant of the Big Bang itself, the very first vibration in the strings of space-time, a direct memory of creation. This would be like adding a sense of hearing to our astronomical toolkit, allowing us to listen to the universe's deepest past instead of just looking at it. But our quest to see further back doesn't stop with gravity. Astronomers are now planning telescopes designed to peer into the cosmic dark ages, the mysterious period before the first stars and galaxies ignited. This era is hidden from traditional telescopes because there was no light to see. The universe was filled with a fog of neutral hydrogen gas. However, that same gas emits a very specific, faint radio signal at a wavelength that has been stretched by the expansion of the universe to around 21 meters. Projects like the Square Kilometre Array Observatory aim to map this signal across the entire sky, creating a 3-dimensional tomographic map of the universe during its infancy. By detecting slight variations in this hydrogen fog, these telescopes will reveal how the first structures began to clump together under the influence of dark matter, showing us the very first whispers of organization in the cosmos, the blueprint from which everything we see today eventually arose. Beyond simply building larger collectors, the real breakthrough will come from a fusion of artificial intelligence and quantum sensing. The data streams from these future observatories will be so immense and complex that no human team could ever hope to sift through them. Advanced AI algorithms trained to recognize subtle patterns and correlations will act as our cosmic translators, deciphering the hidden messages in petabyte upon petabyte of information. They might find connections between the polarization of the cosmic microwave background and the distribution of galaxy clusters that reveal the nature of inflation, or identify the unique signature of a cosmic string in a gravitational wave signal that would otherwise be lost in the noise. At the same time, quantum sensors, leveraging the bizarre properties of entanglement and superposition, will give us detectors of unimaginable sensitivity. These devices could measure the faintest magnetic fields from ancient astrophysical jets or detect the minuscule energy shifts caused by relic particles, opening windows into realms of physics we currently cannot access. The ultimate goal, the holy grail of this entire endeavor, is to move beyond indirect observation and toward a form of cosmic simulation so accurate it borders on time travel. With enough data on the initial conditions of the universe and a complete understanding of the laws of physics, including the elusive theory of quantum gravity, we could one day feed all that information into a hyper-advanced quantum computer. This wouldn't be a simple animation. It would be a true simulation running on the fundamental laws of reality. We could witness the formation of the first star in real time, not as an artist's impression, but as a calculated physical reality. We could watch a galaxy collide with another, seeing exactly how magnetic fields are amplified and how gas is funneled into new stellar nurseries. We could rerun the history of the solar system to see if Earth's water was indeed delivered by comets. This would be the final stage of cosmic archaeology, not just recovering artifacts, but resurrecting the past itself within a digital universe, allowing us to experience the memory of the cosmos not as a static record, but as a living, breathing reality. But beyond the equations and the observations, the quest to understand cosmic memory forces us to confront questions that have haunted philosophers and theologians for millennia. This isn't just a technical puzzle about data storage on a grand scale. It's a profound inquiry into the very nature of reality, time, and our own consciousness. If the universe truly remembers, what does that say about the flow of time? We experience time as a relentless, linear arrow, moving from a fixed past through a fleeting present into an uncertain future. Yet the physical laws governing the universe, from quantum mechanics to general relativity, are largely time-symmetric. They work just as well running backwards as forwards. The difference, the thing that creates the arrow of time, is the growth of entropy and the corresponding preservation of information in the form of memory. Cosmic memory objectifies time. It suggests that the past isn't a ghost that vanishes. It is a physical structure, a series of immutable etchings in the fabric of spacetime. This challenges the view famously proposed by Immanuel Kant, that time is merely a fundamental mental structure through which we perceive the world. Instead, cosmic memory implies time has an independent physical reality outside of our minds, a vast chronicle that exists whether anyone is there to read it or not. This physicalization of history deeply intersects with the ancient philosophical debate between determinism and free will. If every event leaves a permanent, causal mark on the cosmos, then the universe's entire history could be seen as a single, predetermined block, a four-dimensional structure where past, present, and future all equally exist. In this block universe view, our sensation of free will and making choices is an illusion. We are simply following a path that is already written into the cosmic ledger. However, the quantum nature of reality offers a fascinating counterpoint. Quantum mechanics introduces genuine randomness and probability at its foundation. The universe's memory isn't a recording of a predetermined script, but a log of outcomes that were only resolved into reality at the moment of observation. This suggests a cosmos that is writing its story as it goes, with our choices and actions playing a real role in determining which possibilities become actualized and are therefore permanently recorded. We aren't just readers of the cosmic diary, we are its co-authors, our free will expressed through which sentences get permanently inked onto the page of spacetime. The implications also ripple into the realms of religion and spirituality, offering a new perspective on ancient concepts. The idea of a cosmic ledger that meticulously records every action echoes themes found in many religious traditions, from the karma of Eastern philosophies to the Book of Life in Abrahamic faiths. But here, the judgment isn't metaphysical, it's physical. The universe isn't keeping a moral scoreboard, but a causal one. Your actions, the energy you expend, the gravitational influence of your body, the photons you reflect, all of it, no matter how small, creates a tiny but permanent perturbation in the universe's quantum field. You are literally writing yourself into the history of the cosmos, leaving an indelible mark that will, in principle, persist for all time. This provides a scientifically grounded form of immortality. While our consciousness may fade, the physical evidence of our existence, from the carbon atoms we exhale to the gravitational waves our planet's motion creates, becomes a permanent part of the universal record. We are not fleeting visitors in a universe that forgets. We are permanent contributors to its ongoing narrative. This journey of discovery, from decoding gravitational waves to mapping the cosmic microwave background, is more than just scientific progress. It is a monumental step in the universe's journey toward self-awareness. For billions of years, the cosmos expanded, stars burned out, and galaxies collided, all silently recording their history in a language with no reader. Then, on a tiny planet orbiting an average star, complex structures of matter somehow organized themselves in a way that could begin to decode that language. We are the universe's mechanism for understanding itself. The act of a scientist analyzing the light from a quasar is not a separate event from the quasar's explosion. It is the culmination of it. It is the universe 13.8 billion years after its beginning, finally looking back and beginning to read its own diary. This elevates our existence from a meaningless accident in an indifferent void to an integral part of a grand cosmic process of revelation and remembrance. We are the universe remembering what it is, and in doing so, we give meaning not just to our own lives, but to the entire epoch that made our moment of awareness possible. So as we've journeyed from the faint ripples in space-time to the fiery hearts of black holes, from the ancient light of the cosmic microwave background to the spooky connections of quantum entanglement, a breathtaking tapestry has emerged. The universe is not a silent, empty void where events simply vanish. It is a dynamic, participatory archive, rich with history, whispering its stories through a dozen different languages at once. Gravitational waves carry the echoes of violent collisions. The CMB holds a frozen infant picture of creation. Quantum entanglement weaves a web of silent correlations that remember every interaction. Black holes might not destroy information but transform it, while the holographic principle suggests the entire cosmic story is written on a distant, two-dimensional surface. Even the vacuum of space itself, seething with quantum potential, might hold statistical memories of everything that has ever passed through it. This brings us back full circle to the profound insight of John Wheeler, that the universe does not simply happen, but is built up from acts of observation. We are not passive spectators on a pre-recorded cosmic stage. Our very act of looking, of questioning, of measuring, is what helps crystallize potentiality into reality and inscribe that moment into the permanent ledger of the cosmos. We are participants in this grand story, and in tracing the residue of events across space-time, we do more than just advance science. We deepen our own connection to the narrative of existence itself, discovering that we are woven into the very fabric we are trying to read. This is why the quest to understand cosmic memory is so much more than a technical puzzle. It is a fundamental human journey to find our place in the grand scheme of things. Every new detection by an observatory, every theoretical breakthrough, is another page turned in the universe's autobiography. Each discovery peels back another layer of this magnificent, multi-layered archive, revealing a cosmos that is more interconnected, more mysterious, and more mindful of its own past than we ever could have imagined. The investigation is far from over. It's just beginning, so we want to hear from you. Which of these cosmic memory mechanisms fascinates you the most? Is it the idea that a black hole's event horizon is the ultimate quantum hard drive, or that the entire universe could be a holographic projection? Share your thoughts in the comments below. Let's continue this incredible conversation together. And if you want to join us on the next journey into the deepest mysteries of space and time, make sure to subscribe and hit the bell so you